Welcome. Find a comfortable position, let your breathing slow, and allow yourself to drift into the quiet stories of brilliant minds whose names have faded from memory, but whose work shaped the world of mathematics as we know it. Tonight, we journey through centuries and across continents to meet the unsung mathematicians, those who worked in the margins of history, who taught in silence, who preserved knowledge when it might have been lost forever. These are not the names you learned in school. These are the quieter voices, the patient teachers, the careful translators, the ones who built bridges between one generation and the next. Their stories ask us to reconsider what it means to contribute to human knowledge. Sometimes the greatest gift is not a new discovery, but the act of passing wisdom forward, of opening doors for others, of keeping the light of learning alive in dark times. So settle in. Let these stories wash over you like a gentle tide. There is no need to remember every detail. Simply let yourself be carried along by the rhythm of lives well lived, of problems solved in stillness, of truths quietly preserved. We begin our journey in ancient China, in the imperial courts of the Han dynasty, where a remarkable woman would help shape the mathematical education of an empire. Ban Zhao, c. 45 to 116 CE. In the 1st century of the Common Era, in the great cities of Han dynasty China, there lived a woman whose name would become synonymous with learning itself. Ban Zhao. Her name, when spoken, carried the weight of scholarship, of wisdom, of a mind that moved with grace through the complex corridors of classical knowledge. She was born into a family already distinguished by intellectual achievement. Her father, Ban Biao, was a renowned historian, and her brother, Ban Gu, would become one of China's most celebrated chroniclers. But Ban Zhao would carve her own path through history, one that would intertwine with the very foundations of Chinese mathematics and education. Imagine, if you will, the imperial palace in Luoyang, the eastern capital of the Han dynasty. The courtyards are quiet in the early morning, mist rising from ornamental ponds where carp drift like living brushstrokes. Inside the palace halls, silk scrolls lie unfurled on low tables, their surfaces covered with neat columns of characters. This is where Ban Zhao worked, surrounded by the accumulated knowledge of centuries, tasked with a responsibility that would have overwhelmed most scholars of her time. When her brother Ban Gu died in the year 92 CE, leaving his monumental work, the Book of Han, unfinished, it was Ban Zhao who was called upon to complete it. The emperor himself recognized that she possessed not only the knowledge, but the clarity of mind necessary to finish what her brother had begun. The Book of Han was more than a simple historical chronicle. It was an encyclopedia of knowledge, a comprehensive record of the Western Han dynasty that included everything from political history to astronomy, from geography to, crucially, mathematics. Among its many sections was a treatise on mathematics and astronomy that required deep technical understanding to complete. Ban Zhao approached this work with the same meticulous care she brought to all her scholarship. She understood that she was not merely recording facts, but preserving a way of thinking, a methodology that future generations would need. Mathematics in Han Dynasty China was intimately connected with practical governance. To run an empire, one needed to understand astronomy for creating accurate calendars, geometry for land measurement and taxation, arithmetic for commerce and state finance. The mathematical knowledge of the time was encoded in texts like the 9 chapters on the mathematical art, a foundational work that every educated official was expected to master. Ban Zhao knew these texts intimately. She had studied them, worked through their problems, understood their elegant solutions to questions of area, volume, proportion, and distribution. But Ban Zhao's contribution to mathematics went beyond her work on the Book of Han. She became a teacher, perhaps the most influential mathematics teacher in the imperial court. Imagine her in a palace study room, surrounded by the daughters of noble families, and even the empress herself, patiently explaining the principles of calculation, the methods for solving systems of linear equations, the geometric proofs that undergirded land surveying. Her voice would have been calm, measured, moving through complex ideas with a clarity that made the difficult seem approachable. In Chinese mathematical tradition, there was a concept known as chosuan, the art of calculation using counting rods. These were small bamboo or wooden sticks that could be arranged on a counting board to represent numbers and perform operations. It was a sophisticated system, one that allowed for complex calculations including negative numbers and the solution of systems of equations, achievements that would not appear in European mathematics for many centuries. Ban Zhao would have been expert in this method, her fingers moving the counting rods with practiced efficiency, demonstrating to her students how abstract problems could be made concrete, how numbers could be manipulated to reveal hidden truths. What made Ban Zhao truly remarkable, though, was not simply her mathematical knowledge, but her philosophy of education. She understood that knowledge must be transmitted with patience and care. In her famous work, Lessons for Women, written as a guide for female education, she emphasized the importance of humility, diligence, and continuous learning. While this text is sometimes misunderstood through a modern lens, within its pages lies a profound commitment to the idea that women should be educated, should understand mathematics, astronomy, history, and literature. In an era when female education was far from universal, Ban Zhao insisted that intellectual cultivation was essential. Think of her students, young women who might otherwise have been denied access to mathematical knowledge, sitting before counting boards, learning to solve problems that their brothers studied in the Imperial Academy. Ban Zhao taught them that mathematics was not a masculine domain, but a universal language, a tool for understanding the patterns that ran through all of nature and society. She taught them the methods for calculating areas of fields of irregular shapes, for determining fair tax assessments, for predicting celestial events. These were not abstract exercises, but practical skills that connected mathematical understanding to the functioning of the world. The night sky above Luoyang would have been free from the light pollution we know today, stars scattered across the darkness like rice grains spilled on black silk. Ban Zhao understood that those points of light moved according to mathematical principles, that their positions could be calculated and predicted. Astronomy and mathematics were inseparable in Chinese scholarly tradition, and Ban Zhao's work helped ensure that this integrated knowledge would be passed forward intact. Her role at court extended to becoming the most trusted tutor to the Empress Deng Sui. When Empress Deng became regent after the death of her infant son, it was Ban Zhao's education that had prepared her for the intellectual demands of governance. The Empress would consult Ban Zhao on matters of state, on interpretations of classical texts, on decisions that required both moral wisdom and practical calculation. In this way, Ban Zhao's mathematical teaching had direct political impact. The knowledge she transmitted shaped how an empire was governed. But perhaps Ban Zhao's deepest contribution lies in something harder to quantify than any geometric proof or astronomical calculation. She embodied the principle that mathematics is not only discovered but preserved, not only created but transmitted. Every field of human knowledge depends on teachers who can take the innovations of one generation and pass them, intact and understood, to the next. Without such transmission, the most brilliant discoveries die with their discoverers, becoming nothing more than lost fragments, puzzles for future scholars to piece together. Ban Zhao understood this profoundly. When she completed the Book of Han, she was not merely finishing her brother's work. She was ensuring that the mathematical and astronomical knowledge of the Western Han period would not be lost. When she taught in the palace, she was not simply educating individual students. She was creating a lineage of understanding that would ripple forward through time. The students she taught would teach others, who would teach others still, each generation preserving and adding to the accumulated wisdom. In the quiet of her study, by the light of oil lamps, Ban Zhao worked on problems that required both technical skill and deep patience. The mathematical texts she helped preserve were written in classical Chinese, dense with specialized terminology, requiring extensive commentary to be understood. She provided that commentary, those explanations that bridged the gap between terse ancient formulations and living comprehension. This work of explanation, of making knowledge accessible, is itself a form of mathematical contribution, one that is often invisible in historical records, but absolutely essential to the continuity of the discipline. As the years passed and Ban Zhao grew older, her reputation only deepened. She was revered not as a curiosity, a learned woman in a man's world, but as a scholar in her own right, someone whose judgment was trusted, whose interpretations were authoritative. When she died, sometime around the year 116 CE, she left behind a legacy that would influence Chinese education for centuries. The palace women she had taught went on to teach their own children. The mathematical methods she had preserved continued to be studied and refined. And yet, her name gradually faded from the most prominent chronicles of mathematics. Later histories would focus on male scholars, on the inventors of new methods, rather than the preservers of old ones, on the flashy innovations, rather than the patient work of transmission. Ban Zhao became unsung, her contributions assumed rather than celebrated, her name mentioned briefly, if at all, in surveys of Chinese mathematical history. But the work remains. The knowledge she preserved still echoes through every student who learns classical Chinese mathematics. The teaching methods she exemplified, patient, clear, committed to making difficult ideas accessible, still represent the highest ideals of mathematical education. And the principle she embodied, that preservation and transmission are themselves forms of creation, remains as vital today as it was in the courts of Han Dynasty China. As you drift towards sleep, let yourself imagine Ban Zhao in her study, the counting rods clicking softly as she arranges them on the board, her mind moving through a problem with calm precision. There is no urgency, only the steady progress toward understanding. There is no need to prove herself, only the quiet satisfaction of knowledge transmitted, of wisdom preserved, of doors opened for those who will come after. In this image, in this gentle persistence, we find not only a tribute to Ban Zhao, but a reminder of what mathematics can be at its best, a patient unfolding of truth, a gift passed from one hand to another across the centuries. Hypatia of Alexandria, c. 355 to 415 CE. Let us now travel westward, across mountains and deserts and seas, to another great center of learning in the ancient world. Alexandria. The very name conjures images of marble columns, rising against a brilliant Mediterranean sky, of the great lighthouse standing sentinel over busy harbors, of the legendary library where the accumulated knowledge of civilizations was gathered and preserved. It was here, in this cosmopolitan jewel of late antiquity, that another woman would devote her life to mathematics, to teaching, to the preservation and transmission of knowledge across the uncertain boundaries between eras. Her name was Hypatia, and she lived in a time of transformation and tension, when the ancient world was giving way to something new, when old certainties were crumbling and new orders were emerging. Born around the year 355, she was the daughter of Theon, himself a distinguished mathematician and astronomer who served at Alexandria's museum, the research institution that had once been associated with the Great Library. From her earliest years, Hypatia was immersed in the world of learning, surrounded by geometric diagrams and astronomical tables, by the works of Euclid and Ptolemy, by the echoes of Pythagoras and Plato. Picture young Hypatia in her father's study, papyrus scrolls spread across wooden tables, the afternoon light slanting through high windows. Theon would have been a patient teacher, guiding her through the elements of Euclid, that magnificent edifice of logical reasoning that begins with simple axioms and builds, step by careful step, to profound truths about space and number and form. She learned to construct geometric proofs with the elegance that characterized Greek mathematics at its finest, each proposition following inevitably from what came before, creating chains of reasoning as beautiful as they were unbreakable. But Hypatia was not content simply to absorb the knowledge of the past. As she matured, she began to engage with these ancient texts in a deeper way, not as a passive recipient, but as an active interpreter. She understood that the great works of Greek mathematics and astronomy, written centuries earlier, had become difficult for contemporary students to understand. Language had evolved, technical terminology had shifted, and the cultural context that had made certain assumptions obvious to ancient readers was no longer self-evident. These texts needed commentary, explanation, elucidation. They needed someone who could stand between the ancient authors and modern students, making the profound accessible once more. This became Hypatia's life's work. She devoted herself to writing commentaries on the mathematical classics, creating guides that would help students navigate the sometimes cryptic formulations of earlier mathematicians. She worked on Diophantus's Arithmetica, that remarkable exploration of what we would now call number theory and algebraic equations. Diophantus had investigated problems of finding rational solutions to polynomial equations, work that was centuries ahead of its time in its sophistication. But his notation was cumbersome, his explanations often terse. Hypatia's commentary helped illuminate his methods, making them comprehensible to a new generation. She also prepared editions of Ptolemy's Almagest, the great astronomical treatise that attempted to describe the motions of the heavens with mathematical precision. The Almagest was a work of staggering complexity, combining geometric models with numerical tables, trigonometric calculations with philosophical arguments about the nature of celestial motion. To truly understand it required not just mathematical skill, but physical intuition, astronomical observation, and philosophical sophistication. Hypatia possessed all of these. Her edition of the Almagest included clarifications and explanations that helped students grasp not just what Ptolemy had concluded, but how he had reasoned his way there. Imagine Hypatia at work on such a commentary, sitting in a quiet room as evening settles over Alexandria. Before her lies a scroll of Ptolemy's text, its Greek characters carefully formed in dark ink. She traces a finger along a particularly dense passage about epicycles and deferents, those nested circles that ancient astronomers used to model planetary motion. She pauses, thinking about how to explain this to students who have never spent long nights observing the wandering stars, who don't yet have the intuition that comes from watching Mars trace its peculiar loop against the background of fixed stars. She dips her pen in ink and begins to write in the margin, creating a verbal bridge between Ptolemy's world and theirs. But Hypatia was not only a commentator and editor. She was, above all, a teacher. Students came to her from across the Mediterranean world, drawn by her growing reputation as the most brilliant mathematical mind in Alexandria. She taught in the tradition of the ancient philosophical schools, gathering students around her for lectures and discussions that ranged freely across mathematics, astronomy, and philosophy. These were not dry recitations of theorems, but living explorations of ideas, conversations where questions were welcomed and understanding was built collaboratively. Her lecture hall would have been a simple room, perhaps with benches arranged in a semicircle, the walls bare except for a large board where geometric figures could be drawn and erased and drawn again. Hypatia would stand before her students, explaining the properties of conic sections, those elegant curves that emerge when a plane slices through a cone at different angles. The circle, the ellipse, the parabola, the hyperbola. Each had been studied by the great geometer Apollonius centuries earlier, but Hypatia brought them alive again, showing how these abstract curves appeared in the real world, in the paths of thrown objects, in the orbits of planets, in the focusing properties of mirrors. Her students loved her not just for her knowledge, but for her method. She encouraged them to think for themselves, to question, to explore alternative approaches to problems. She taught them that mathematics was not a collection of dead facts to be memorized, but a living discipline, a way of thinking that could be applied to understanding the world. When a student struggled with a proof, she would guide them gently toward insight, rather than simply providing the answer. She understood that true learning happens not when information is transferred, but when understanding is awakened. In the Neoplatonic tradition that flourished in late antique Alexandria, mathematics held a special place. It was seen as a bridge between the material world and the realm of pure ideas, a discipline that trained the mind to ascend from concrete particulars to abstract universals. Hypatia embraced this philosophical framework. For her, teaching mathematics was not merely technical training, but spiritual cultivation. When her students worked through a geometric proof, they were learning to recognize eternal truths, patterns that existed independent of the physical world, structures of pure logic that reflected the fundamental order of reality itself. But Hypatia lived in dangerous times. Alexandria in the late 4th and early 5th centuries was a city torn by religious conflict. Christianity had become the dominant religion of the Roman Empire, and different Christian factions competed bitterly with one another and with the remaining adherents of traditional Greco-Roman religion. Hypatia, though likely not religious in any conventional sense, became identified with the old pagan learning, with the classical tradition of philosophy and mathematics that some Christian authorities viewed with suspicion. She maintained friendships and correspondences with prominent Christians, including the prefect Orestes who governed Alexandria. She seems to have moved easily between different communities, respected for her learning and her character regardless of religious boundaries. Her lecture hall welcomed students of all backgrounds. Mathematics, after all, was universal, a geometric proof convinced not through religious authority, but through the inherent power of logical necessity. Yet the very universality of her teaching, her refusal to be bound by sectarian divisions, made her vulnerable in a city increasingly defined by such divisions. There were those who saw her influence as a threat, who viewed the classical learning she represented as incompatible with their vision of a Christian society. Tensions rose. The political situation in Alexandria grew volatile, with rival factions jockeying for power and influence. Through it all, Hypatia continued to teach. Every morning, she would make her way through the streets of Alexandria to her lecture hall, her mind already organizing the day's material. Perhaps she would work through problems from Diophantus with her more advanced students, exploring the beautiful symmetries that emerge in certain equations. Perhaps she would guide beginners through the fundamentals of Euclidean geometry, helping them understand why parallel lines never meet, why the angles of a triangle must sum to 2 right angles. The specific content varied, but the underlying purpose remained constant: to preserve and transmit the mathematical heritage of the ancient world, to keep alive the flame of rational inquiry. She also worked on astronomical instruments, applying her mathematical knowledge to practical devices. She is credited with helping to design an astrolabe, that ingenious analog computer that could be used to solve problems of spherical astronomy, to determine the positions of stars and planets, to calculate times for sunrise and sunset. The astrolabe was mathematics made tangible, geometric principles embodied in brass and wood, a tool that allowed observers to hold the heavens in their hands. There was an elegance to Hypatia's life, a coherence between her philosophical commitments and her daily practice. She lived simply, devoted to her students and her work, seeking truth through reason and observation. Those who knew her spoke of her remarkable character, her intellectual fearlessness combined with personal modesty, her ability to engage with complex ideas while maintaining clarity of expression. On quiet evenings, after her students had departed, Hypatia might climb to the roof of her house to observe the night sky. Alexandria's skies, though not as dark as the desert beyond the city, still offered a spectacular view of the cosmos. She would trace the familiar constellations, note the positions of the planets among the fixed stars, perhaps make observations for the astronomical tables she was compiling. This was mathematics in its purest form, the mind reaching out to comprehend the vast patterns that govern celestial motion, finding order in apparent chaos, discovering the geometric principles underlying the dance of the heavens. Her work on conic sections had practical astronomical applications. The ellipse, which Apollonius had studied as a purely abstract geometric object, would later be recognized by Kepler as the actual shape of planetary orbits. Hypatia could not have known this. It would be more than 1,000 years before Kepler made that discovery. But in studying the properties of the ellipse, in understanding how foci and directrices determine its shape, she was laying groundwork, preserving knowledge that would eventually help unlock the secrets of celestial mechanics. This is what it means to preserve and transmit knowledge across generations. Hypatia could not foresee all the ways her work would matter. She could not know which seeds she planted would bear fruit centuries later. But she understood that the work itself was valuable, that keeping the tradition of mathematical reasoning alive was essential, regardless of immediate practical applications. Mathematics was a form of knowledge worth preserving for its own sake, as part of humanity's attempt to understand the universe we inhabit. The political tensions that swirled around her could not be solved by geometric proofs or astronomical calculations. In March of 415 CE, a mob attacked Hypatia as she travelled through the city. She was killed, her death a brutal ending to a life devoted to learning and teaching. The details of that day are too harsh for this peaceful space, but the loss was immeasurable, not just of a brilliant individual, but of everything she might have taught in the years that remained, the commentaries she might have written, the students she might have inspired. Yet her legacy endured. The commentaries she wrote survived, copied and recopied by scribes through the medieval period, eventually making their way to the Renaissance when interest in classical mathematics revived. Students in Baghdad and Constantinople would study texts that bore her explanatory notes. The methods she taught, the approaches to mathematical problems she exemplified, became part of the living tradition that connected the ancient world to the modern. Hypatia stands as a bridge, her life spanning the transition from classical antiquity to the medieval world, her work helping to preserve the mathematical achievements of Greece and Alexandria through a period of tremendous upheaval. Like Zhao before her, she understood that the greatest contribution one can make is not always the discovery of new truths, but the careful preservation and transmission of old ones, making them accessible to new generations who will build upon that foundation. As sleep approaches, let the image of Hypatia settle in your mind, standing before her students, chalk in hand, drawing a perfect circle on the board, her voice calm and measured as she explains why this simple closed curve has such profound properties. In that moment of teaching, in that transfer of understanding from one mind to another, mathematics becomes what it was always meant to be. Not a solitary achievement, but a collective endeavor, a conversation across centuries, a light passed from hand to hand through the darkness of time. Thomas Harriot, circa 1560 to 1621. Now we move forward through the centuries, from the Mediterranean world of late antiquity to the England of the Renaissance, a time when mathematics was being reborn in Western Europe, when ancient texts were being rediscovered and new methods were being invented. It is an age of exploration, both geographical and intellectual. Ships are sailing to unknown continents, telescopes are turning toward the heavens, and mathematics is becoming a tool not just for philosophy, but for navigation, commerce, and the emerging sciences. In this world of rapid change and new possibilities, there lived a man whose mathematical brilliance would be recognized fully only centuries after his death, whose discoveries would be made and then hidden away, whose story reminds us that even the most profound ideas can vanish into silence if they are not shared. His name was Thomas Harriot, and he was perhaps the most gifted English mathematician of his age, working in the shadow of Galileo and Kepler on the continent, yet making discoveries that would have astonished them had they known. Born around 1560, likely in Oxford, Harriot came of age in Elizabethan England, that era of Shakespeare and Drake, of the Spanish Armada, and the first tentative English colonies in the New World. He was educated at Oxford University, where he studied the mathematical arts, arithmetic, geometry, astronomy, and the practical applications of these disciplines to navigation and surveying. After completing his studies, Harriot entered the service of Sir Walter Raleigh, that restless adventurer and courtier who dreamed of establishing English power across the Atlantic. In 1585, Harriot sailed with Raleigh's expedition to Roanoke Island, off the coast of what is now North Carolina, serving as the expedition's surveyor and scientific observer. Imagine him on the deck of the ship during that long Atlantic crossing, sextant in hand, measuring the altitude of the sun at noon, calculating their latitude, recording observations that would help create more accurate maps and navigation tables. In the New World, Harriot encountered peoples and landscapes utterly unlike anything he had known in England. He learned the Algonquian language, studied the customs and knowledge systems of the indigenous peoples, recorded information about the flora and fauna of this new land. He was that rare combination, a mathematician with genuine curiosity about the world in all its variety, someone who saw connections between abstract calculation and lived experience. His maps and reports from the Roanoke voyage demonstrated a meticulous attention to detail, a refusal to rely on assumption or hearsay when direct observation was possible. But it was after his return to England that Harriot's mathematical genius truly flourished. He became part of a remarkable intellectual circle that gathered around Henry Percy, the Earl of Northumberland, known as the Wizard Earl, for his interest in the new sciences. Percy provided Harriot with financial support and the freedom to pursue his research without the pressures of earning a living through teaching or other employment. This was an extraordinary gift, the time and security to think deeply, to follow mathematical problems wherever they led, to work at his own pace on questions that fascinated him. Harriot settled into a routine of study and discovery. His rooms became filled with papers covered in calculations, astronomical observations, algebraic equations, optical diagrams. He corresponded with other mathematicians across Europe, though less extensively than he might have. And here we encounter the central puzzle of Thomas Harriot's life. Despite making extraordinary discoveries, he published almost nothing during his lifetime. While Galileo was publishing his telescopic observations and Kepler his laws of planetary motion, Harriot was quietly filling thousands of pages of manuscript with ideas that would not be widely known for centuries. Let us enter Harriot's study on a quiet evening in London, perhaps in the year 1609. Candles flicker on his desk, casting moving shadows across the papers spread before him. He is working on problems in algebra, developing a new symbolic notation that makes it easier to manipulate equations and see their underlying structure. Previous mathematicians had written out algebraic problems in words, long, cumbersome sentences describing mathematical relationships. Harriot was developing a system where symbols could stand for unknown quantities, where equations could be written concisely and operated upon almost mechanically. Look at his notation. He uses lowercase letters to represent unknown quantities. He writes equations with both sides separated by what would become our equals sign. He develops systematic methods for solving polynomial equations, going beyond what was known to his contemporaries. He discovers what we now call the fundamental theorem of algebra in a special case, that a polynomial equation of degree n has n roots, though some may be repeated or complex. These insights would not be fully formalized until the 19th century, yet here is Harriot, in the early 17th century, glimpsing these truths through his algebraic investigations. But he doesn't publish this work. The manuscripts pile up on his desk, in his cabinets, carefully organized, but never sent to a printer. Why? The reasons are complex, and perhaps not fully recoverable across the centuries. Partly, it seems, Harriot was a perfectionist, always wanting to refine his ideas further before exposing them to public scrutiny. Partly he may have been cautious about the political and religious controversies that could arise from scientific work. His patron, the Earl of Northumberland, was imprisoned in the Tower of London for years due to suspected involvement in the Gunpowder Plot, and Harriot himself was briefly imprisoned and investigated for atheism. But there may have been something else too, a kind of intellectual isolation, a preference for the private satisfaction of discovery over the public claims of priority. Harriot seems to have delighted in solving problems for their own sake, in seeing patterns emerge from calculations, in the pure joy of mathematical insight. The thought of preparing treatises for publication, of defending his methods against critics, of entering into the contentious world of scholarly debate, may simply have held no appeal for him. Meanwhile, he was making astronomical observations that paralleled and sometimes preceded those of Galileo. In the summer of 1609, Harriot constructed one of the first telescopes in England, shortly after hearing reports of the Dutch invention. By July of that year, he was turning his telescope toward the moon, making detailed drawings of the lunar surface. His sketches show the moon not as a perfect sphere, but as a world with mountains and valleys, with rough terrain casting shadows that change with the angle of sunlight. These observations were made several months before Galileo's more famous lunar observations, yet Harriot never published them. Picture him on a clear night, standing in the garden of his residence at Sion House, the telescope mounted on a simple stand. The summer air is still warm, carrying the scent of night-blooming flowers. He adjusts the telescope, bringing the moon into focus, and there it is, not the smooth, luminous disk of poetic description, but a complex landscape, craters and bright rays and dark plains. He sketches quickly, recording what he sees before the moon's rotation, and his own changing perspective alter the pattern of shadows. Night after night he returns to these observations, building up a detailed map of the lunar surface. He also observed the moons of Jupiter, those 4 bright points that orbit the giant planet, their positions changing from night to night in a stately dance governed by mathematical law. He tracked sunspots, those dark blemishes on the sun's surface that revealed the star at the center of our solar system was not perfect and unchanging, but dynamic and complex. He studied the phases of Venus, which provided crucial evidence for the Copernican model of the solar system. All of this Harriot saw and recorded, yet he shared it only with a small circle of correspondents, never presenting it to the wider world of learning. In his optical researches, Harriot discovered the law of refraction, the mathematical relationship that describes how light bends when passing from one medium to another, such as from air into water or glass. This is the principle underlying lenses, rainbows, the apparent bending of a stick when placed in water. Harriot worked out this law around 1602, expressing it mathematically with his characteristic precision. Yet he did not publish it. 20 years later, Willebrord Snellius would rediscover the same law, and it would eventually be published by René Descartes, who gets much of the credit in history books. Harriot's discovery remained buried in his manuscripts. The same pattern repeats across different domains of mathematics and science. Harriot made advances in the theory of equations, in analytic geometry, in numerical methods for solving problems. He developed techniques that would not become widely known until other mathematicians, working independently, rediscovered them decades or centuries later. In his manuscripts, we can see him working toward ideas that would only find full expression in the work of Descartes, Newton, and Euler. He was ahead of his time, but his ideas remained locked away, accessible only to the few who could examine his papers directly. Consider what was lost. If Harriot had published his algebraic methods in, say, 1610, they would have been available to the generation of mathematicians that included Descartes and Fermat. The development of analytic geometry and algebraic techniques might have accelerated by decades. His astronomical observations, if widely disseminated, would have provided independent confirmation of the discoveries Galileo was announcing, strengthening the case for the new astronomy. His optical law, if published, might have sparked earlier developments in the theory of light and the construction of better telescopes and microscopes. But this did not happen. Harriot continued his solitary work, filling manuscript after manuscript with calculations and observations, diagrams and theorems. In 1621, he died of cancer, leaving behind an enormous collection of unpublished papers. His executors recognized that these papers contained valuable material, and they arranged for some of it to be published. In 1631, a work called Artis Analyticae Praxis appeared, presenting some of Harriot's algebraic methods. But this was only a fraction of his work, and even this partial publication came a decade after his death, too late to have the impact it might have had. The rest of his manuscripts were preserved, but not published. They were studied by a few scholars over the centuries, but they never entered the mainstream of mathematical development. It was not until the 20th century that historians of mathematics began to fully appreciate the scope and depth of Harriot's achievements, going through his papers systematically and recognizing just how much he had anticipated later discoveries. By then, of course, these ideas had long since been rediscovered by others and integrated into mathematics through different routes. Harriot's story raises profound questions about the nature of mathematical progress and historical recognition. Is a discovery truly a discovery if it is never shared? Does a proof exist, in any meaningful sense, if it remains in a desk drawer unseen by other mathematicians? Mathematics, unlike some forms of art or literature, is fundamentally a collective endeavor. A mathematical truth is not just something one person knows. It becomes part of mathematics only when it is communicated, verified, built upon by others. This is the poignant lesson of Thomas Harriot's life. He had a mind capable of profound insights, a dedication to careful observation and rigorous reasoning, the freedom to pursue his research wherever it led. But by choosing not to share his discoveries, by keeping his work private, he effectively removed himself from the historical development of mathematics. His ideas had to wait to be rediscovered, and when they were, the credit went to others. Yet perhaps there is something admirable, too, in Harriot's approach. He pursued mathematics for its own sake, not for fame or recognition. He found satisfaction in the work itself, in the moment of understanding when a difficult problem yields to analysis, in the beauty of an elegant proof or a precise observation. In our modern world, so focused on publication metrics and priority disputes, there is something refreshing about a mathematician who simply wanted to think, to calculate, to observe, without concern for external validation. Imagine Harriot in his final years, knowing he is ill, looking at the stacks of manuscripts that represent decades of work. Does he regret not having published more? Or does he find peace in having lived according to his own values, having pursued knowledge for its own sake? We cannot know, but we can recognize in his story a reminder that mathematics exists in a tension between individual insight and collective knowledge, between private understanding and public discourse. As you settle deeper into rest, let the image of Harriot's study remain with you. The papers covered with equations, the telescope by the window, the candles burning low. There is a melancholy beauty in this scene, in all that brilliant work done in quiet isolation. It reminds us that knowledge, no matter how profound, needs to be shared to truly matter, needs to move from one mind to another to become part of humanity's collective understanding. Harriot's ideas eventually found their way into Muhammad ibn Musa al-Khwarizmi, c. 780 to 850. Let us journey now eastward and back through time, to a place and era where knowledge from across the known world converged and transformed. Baghdad, in the early 9th century, was the jewel of the Abbasid Caliphate, a city of perhaps 1 million souls, its markets bustling with merchants from China and India, from Persia and Byzantium, from North Africa and the distant lands beyond the Sahara. The great Tigris River flowed through its heart, its waters carrying boats laden with goods and ideas. And in this cosmopolitan center of trade and culture, there arose an institution that would become one of history's great centers of learning. The House of Wisdom, Beit al-Hikmah, where scholars gathered to translate, study, and extend the accumulated knowledge of civilizations. It was here, in this atmosphere of intellectual ferment and cultural exchange, that a scholar named Muhammad ibn Musa al-Khwarizmi worked and taught, creating books that would fundamentally shape how mathematics would be practiced and understood for the next 1,000 years and beyond. His name, Al-Khwarizmi, tells us he came from Khwarazm, a region south of the Aral Sea in what is now Uzbekistan, but his legacy would be truly universal, spreading from the Maghreb to the Indonesian archipelago, from the Islamic world to Christian Europe, becoming so deeply embedded in Western mathematics that we use forms of his name every day without realizing it. Picture the House of Wisdom on a warm Baghdad morning, sunlight streaming through latticed windows into rooms lined with shelves holding manuscripts in Arabic, Greek, Sanskrit, and Persian. Scholars move quietly through these spaces, some bent over texts, carefully translating ancient works into Arabic. Others engaged in discussion, debating the merits of different approaches to astronomical calculation or geometric proof. Al-Khwarizmi is among them, a man in his prime, perhaps 30 or 40 years old, his mind occupied with a question that has engaged mathematicians across cultures. How can we systematically solve problems involving unknown quantities? The Greeks had approached such problems geometrically, visualizing unknowns as lengths or areas. Indian mathematicians had developed sophisticated arithmetic and algebraic techniques, working with negative numbers and sophisticated numerical methods. Chinese mathematicians had their own approaches, using counting rods and matrix-like arrays to solve systems of equations. Al-Khwarizmi had studied all these traditions. The House of Wisdom was precisely the kind of place where such cross-cultural synthesis was possible. Now he set himself the task of creating something new, a systematic, step-by-step method for solving equations, one that could be taught to students and applied to practical problems in commerce, inheritance law, surveying, and engineering. Around the year 820, Al-Khwarizmi completed a book with a title that would echo through history, Kitab al-Jabr wal-Muqabala, the Book of Restoration and Balancing. From al-Jabr, the restoration, comes our word algebra. The book was revolutionary not because the individual techniques it contained were entirely new, many had been known to earlier mathematicians, but because of how Al-Khwarizmi organized and presented them. He created a systematic framework, a logical progression from simple to complex, with clear explanations and worked examples. This was mathematics as a teachable discipline, mathematics structured for learning and application. Imagine Al-Khwarizmi at work on this text, sitting in a quiet corner of the House of Wisdom, reed pen in hand, a sheet of parchment before him. He is explaining how to solve what we would write as a quadratic equation, something like x superscript 2 plus 10x equals 39. But he writes it out in words, describing the problem in clear, concrete terms. A square and 10 roots equal 39 dirhams. He then walks the reader through the solution step by step. Take half the number of roots, which is 5, multiply it by itself, getting 25, add this to the 39, getting 64, and take the square root, which is 8. From this subtract the half of the roots, 5, leaving 3, which is the answer, the root, or what we would call the unknown. But Al-Khwarizmi doesn't just give mechanical rules. He explains why these procedures work, providing geometric demonstrations that show the underlying logic. He draws squares and rectangles, showing how the algebraic operations correspond to manipulations of areas and lengths. This connection between algebra and geometry, between numerical calculation and visual understanding, makes his work accessible to students with different styles of learning. Some might grasp the problem through the geometric pictures, others through the arithmetic procedures, but both paths lead to the same truth. The structure of his algebra book is careful and deliberate. He begins with the simplest types of equations, those involving just squares and roots, or just squares and numbers, or just roots and numbers. Then he progresses to equations combining all three elements. For each type, he provides multiple worked examples, showing how to apply the methods to different problems. This pedagogical approach, moving from simple to complex, providing abundant examples, explaining the reasoning behind procedures, would become a model for mathematics textbooks down through the centuries. But Al-Khwarizmi's influence extends far beyond algebra. He also wrote a treatise on the decimal number system and calculation methods that had been developed in India. This book, whose original Arabic version is lost, but which survives in Latin translations, introduced European scholars to the numeral system we still use today. the digits 0 through 9, place value notation, and efficient algorithms for arithmetic operations. The Latin translations of this work began with phrases like algorithmi dicit, Al-Khwarizmi says, and from this the word algorithm emerged, meaning a step-by-step procedure for solving a problem. Think about what this means. Every time we perform long division, every time we add columns of numbers, every time a computer executes a program, these are all algorithms in the sense that Al-Khwarizmi helped establish. The very idea that mathematical procedures can be broken down into precise, mechanical steps that anyone can follow, this fundamental insight underlies all of modern computation. Al-Khwarizmi didn't invent arithmetic algorithms from nothing. Indian mathematicians had developed many of these techniques, but he systematized them, explained them clearly, and transmitted them to a wider world. In quiet moments, perhaps Al-Khwarizmi reflected on the deeper significance of his work. Mathematics, he understood, could be a universal language, transcending the boundaries of empire and culture. A geometric proof convinces through logic, not through authority. A correctly solved equation gives the right answer whether the solver is in Baghdad or Cordoba, in Delhi or Damascus. By creating clear, systematic presentations of mathematical methods, he was building bridges across which knowledge could travel. He also worked on astronomy and geography, creating tables for calculating the positions of the sun, moon, and planets, and producing an improved world map based on Ptolemy's geography, but updated with more recent information from Islamic travelers and traders. These were practical works, meant to be used by astronomers making calendars, by merchants planning voyages, by administrators surveying lands. Al-Khwarizmi saw no sharp division between pure and applied mathematics. Both were part of the same enterprise of understanding and working with the world. The House of Wisdom, where Al-Khwarizmi worked, was itself a testament to the power of knowledge sharing. The Abbasid caliphs who founded and supported it understood that intellectual achievement brought prestige and practical benefits. They sponsored the translation of works from Greek, Sanskrit, Syriac, and Persian into Arabic, preserving texts that might otherwise have been lost and making them available to a new generation of scholars. They brought together astronomers and mathematicians, physicians and philosophers, creating an environment where cross-pollination of ideas could happen naturally. In this environment, Al-Khwarizmi could draw on the mathematical traditions of Greece, India, and Persia. He could compare different approaches to the same problem, selecting what worked best from each tradition. His algebra, for instance, combined Greek geometric reasoning with Indian arithmetic techniques and Persian practical problem-solving. The result was something greater than the sum of its parts, a new synthesis that would prove enormously fruitful. The spread of Al-Khwarizmi's works followed the networks of trade and scholarship that connected the medieval Islamic world. His algebra was studied in Cordoba and Cairo, in Isfahan and Samarkand. Students copied out his texts by hand, adding their own commentaries and worked examples. Teachers used his book as a foundation for their own lectures, explaining the methods to new generations of students. Practical people, merchants calculating profits, tax collectors dividing inheritances, engineers planning irrigation systems, all found Al-Khwarizmi's methods useful in their daily work. In the 12th century, European scholars began translating Arabic mathematical and scientific works into Latin, and Al-Khwarizmi's treatises were among the first and most influential to be translated. Robert of Chester produced a Latin version of the algebra book in 1145. These Latin translations introduced medieval European scholars to both the methods and the terminology, algebra, algorithm, and even zero, from the Arabic cifr, entered European languages through this transmission. Think of a medieval European student, perhaps in Paris or Oxford in the 13th century, encountering Al-Khwarizmi's algebra for the first time. The strange new terminology, the systematic approach to solving equations, the Hindu-Arabic numerals that made calculation so much more efficient than Roman numerals. All of this would have seemed revolutionary. And indeed it was. These tools would become foundational for the scientific revolution that would transform Europe in the following centuries. But Al-Khwarizmi himself would have known nothing of this future influence. He lived and worked in 9th century Baghdad, writing for his contemporaries, trying to create useful and clear presentations of mathematical methods. His satisfaction came from the work itself, from finding the right way to explain a difficult concept, from organizing material in a logical progression, from seeing students grasp ideas that had previously confused them. On a quiet evening in Baghdad, after the day's work at the House of Wisdom was done, Al-Khwarizmi might have walked along the banks of the Tigris, watching the sun set over the city, turning the river to gold. The markets would be closing, the call to evening prayer echoing from minarets. Tomorrow he would return to his manuscripts, to the patient work of writing and explaining, teaching and clarifying. He was building something that would last, though he could not have imagined just how far into the future his influence would extend. His legacy is unusual among our unsung mathematicians because his name has survived, embedded in words we use constantly, algebra and algorithm. Yet most people who use these words have no idea who Al-Khwarizmi was, what he actually wrote, or how his work transformed mathematics. He is simultaneously famous and forgotten, his influence everywhere, and his actual story known to few. What Al-Khwarizmi demonstrated was that mathematics could be structured for teaching, that complex methods could be broken down into learnable steps, that knowledge from different cultures could be synthesized into coherent systems. He showed that the purpose of mathematical writing was not just to record discoveries, but to enable others to understand and apply those discoveries. In this sense, he carried forward the tradition we saw in Zhao and Hypatia, the commitment to transmission and teaching, while also creating something new, mathematics as a systematic discipline with standardized methods and universal applicability. As sleep draws near, envision the House of Wisdom in its golden age, scholars from across the world working side by side, translating and commenting, calculating and theorizing. Among them sits Al-Khwarizmi, writing with careful precision, creating the foundations of modern mathematics one patient line at a time. His pen moves steadily across the page, forming the elegant curves of Arabic script, explaining how to restore and balance, how to solve and understand. The work is quiet, methodical, and enduring. In this image of patient scholarship, of careful systematization, of knowledge freely shared and clearly explained, we find mathematics at its most generous, a gift offered to all who wish to learn, a bridge connecting minds across the centuries. Adolphe Quetelet, 1796 to 1874. We move forward now through time, across centuries of mathematical development, to 19th century Europe, an age of transformation unlike any before it. Steam engines are reshaping industry and transportation. Cities are growing at unprecedented rates. Nations are collecting data about their citizens, births and deaths, crimes and marriages, heights and weights, creating vast tables of numbers that cry out for interpretation. In this world of rapid change and accumulating statistics, a Belgian astronomer and mathematician would pioneer a new application of mathematics, one that would prove both powerful and troubling: the mathematical study of human beings themselves. His name was Adolphe Quetelet, and he was born in Ghent in 1796, just as the revolutionary upheavals that had transformed Europe were giving way to a new order. He came of age in a world fascinated by measurement and classification, by the possibility that the same mathematical tools that had unlocked the secrets of planetary motion might also reveal patterns in human society. Quetelet would spend his life pursuing this vision, applying the methods of astronomy and probability theory to questions about crime and mortality, body measurements, and social behavior. In doing so, he would help create the field we now call statistics, and raise profound questions about what it means to reduce human complexity to numbers and averages. Picture young Quetelet in the 1820s, newly appointed as director of the Royal Observatory of Brussels. The observatory is still being built, and while he waits for its completion, Quetelet travels to Paris to study with the great astronomers and mathematicians of France. There he encounters the work of Laplace and Fourier, learns about probability theory, and the method of least squares for dealing with observational errors. He sees how astronomers handle the inevitable imperfections in their measurements, taking multiple observations, calculating averages, understanding that individual measurements scatter around some true value according to predictable patterns. And then Quetelet has an insight, one that will shape the rest of his career. If astronomical measurements scatter according to mathematical laws, might not human measurements do the same? If we collect enough data about people, their heights, their chest circumferences, their ages at death, might we find similar patterns, the same bell-shaped curves that describe observational errors in astronomy? Could we, in short, apply the mathematics of the physical sciences to the study of human beings? This idea leads Quetelet to begin collecting data with unprecedented thoroughness. He gathers statistics on crime rates in France, noticing that certain types of crimes occur with remarkable regularity year after year. He collects measurements of Scottish soldiers' chest sizes, finding that they distribute in a bell curve around an average value. He examines mortality tables, birth records, marriage statistics, looking always for mathematical regularities hidden in the mass of individual cases. Imagine Quetelet in his study, surrounded by tables of numbers, meticulously copied from government reports and official records. The afternoon light slants through the windows as he works his way through columns of figures, calculating averages and distributions, searching for patterns. Here is a table showing the number of crimes committed in each age group. Here another showing how height varies across a population. The individual numbers seem chaotic, but when he plots them, when he calculates averages and measures of dispersion, patterns emerge. The data forms curves, follows laws, exhibits regularities that can be expressed mathematically. From these observations, Quetelet develops his most famous concept, l'homme moyen, the average man. This is not a real person, but a statistical construct. The individual who sits at the center of all distributions, possessing average height, average weight, average proportions. Quetelet argues that this average man represents a kind of ideal, that nature aims at this central type, and that individual variations are deviations from this target, errors distributed according to the same laws that govern errors in astronomical observation. Consider what this means. When an astronomer measures the position of a star, small errors creep in: atmospheric disturbance, imperfections in the instrument, the limitations of human perception. These errors scatter around the true position in a pattern described by what we now call the normal distribution, or bell curve. Quetelet is suggesting that individual human beings are like these erroneous measurements, scattered around some ideal type, the average man, by the play of countless small influences. The tall person, and the short person are both deviations from the average, just as an observation slightly to the left or right of a star's true position is an error. This is a remarkable intellectual leap, and it proves enormously influential. Quetelet's work helps establish statistics as a legitimate scientific discipline. He shows that social phenomena, crime, suicide, marriage, exhibit regularities that can be studied mathematically. He demonstrates that we can make predictions about populations, even when individual behavior seems unpredictable. If we know the average crime rate and how it varies, we can forecast roughly how many crimes will occur next year, even though we cannot predict which specific individuals will commit them. But there is something troubling here too, something Quetelet himself seems not to fully grasp. When we treat human variation as error around an average, when we describe individual differences as deviations from an ideal type, we risk losing sight of human diversity as valuable in itself. We create a framework where average becomes normal, and normal becomes desirable, and anything far from average becomes suspect or problematic. This way of thinking will have consequences that extend far beyond Quetelet's own work, influencing eugenics, standardized testing, and countless other attempts to measure and categorize human beings. Yet we should not judge Quetelet too harshly. He lived in an age of enormous social problems, poverty, disease, crime, and he genuinely believed that careful measurement and statistical analysis could help address these issues. If we could identify the social conditions that increased crime rates or mortality, we could work to change those conditions. If we could measure the health of populations, we could track whether reforms were succeeding. Mathematics, in this view, was a tool for social improvement, a way of bringing rationality and evidence to questions of public policy. Quetelet's work on what he called social physics was ambitious in scope. He collected data on everything from the seasonal variation in birth rates to the relationship between education and crime. He corresponded with statisticians and social reformers across Europe, sharing methods and findings, building a community of scholars interested in applying mathematical methods to social questions. He organized international conferences on statistics, helping to standardize how different countries collected and reported data. In the quiet of evening, after a day spent with numbers and calculations, Quetelet might reflect on the peculiar nature of his work. He was an astronomer by training, comfortable with the mathematical regularity of celestial mechanics, the predictable orbits of planets and comets. Now he was finding similar regularities in human affairs, but with a difference. The planets had no choice about their orbits. They followed physical laws with perfect necessity. Human beings, in contrast, exercised free will, made choices, acted on intentions and desires. Yet in the aggregate, human behavior showed statistical patterns as reliable as any physical law. What did this mean? Was free will an illusion? Or did individual freedom somehow coexist with collective predictability? Quetelet wrestled with these philosophical questions, never quite resolving them to his own satisfaction. He wanted to believe in both human agency and social laws, in both individual uniqueness and statistical regularity. Perhaps, he suggested, free will operated at the individual level while necessity governed populations. Each person might choose freely whether to commit a crime, but the total number of crimes would still follow predictable patterns because individual choices were influenced by social conditions that affected everyone similarly. His influence on later statistics and social science was profound. Florence Nightingale used his methods to analyze mortality data and advocate for hospital reform. Francis Galton extended Quetelet's ideas in developing regression analysis and correlation, though Galton would take the work in troubling directions with his eugenics program. Émile Durkheim's sociological analysis of suicide rates built on Quetelet's demonstration that even apparently individual acts showed collective patterns. The entire modern infrastructure of social statistics, census bureaus, public health monitoring, economic indicators, descends in part from Quetelet's pioneering work. He also made a lasting contribution to public health through his development of the body mass index, though he did not call it that. Quetelet noticed that, for adults of normal build, weight tended to be proportional to the square of height. He proposed the ratio of weight to height squared as a simple measure of whether someone was above or below average build. This Quetelet index would later be renamed BMI and become one of the most widely used health metrics in the world, despite various limitations that Quetelet himself might have acknowledged had he seen how it would be applied. Picture Quetelet in his later years, now an established figure in European science, his statistical methods widely adopted, his concept of the average man influencing thinkers across disciplines. He attends conferences, delivers lectures, corresponds with fellow scientists. But does he recognize the double-edged nature of what he has created? The power of statistics to reveal truth, and the power of statistics to obscure it, to reduce human complexity to numbers that may not capture what truly matters. There is a scene we might imagine. Quetelet walking through the streets of Brussels on a grey afternoon, passing people of all sorts, tall and short, young and old, healthy and infirm. Each is an individual, unique, with their own story and circumstances. Yet in his statistician's mind, he cannot help but see them also as data points, distributed around averages, following predictable patterns. A young man hurries past. Is he near the average age for marriage? Quetelet wonders. An elderly woman sits begging. She represents the tale of the age distribution, and perhaps also the correlation between poverty and mortality that shows up so starkly in the data. This dual vision, seeing both the individual human being and the statistical aggregate, characterizes Quetelet's legacy. He showed us that we could study human society with mathematical rigor, that patterns existed in social phenomena that could be measured and analyzed. But he also initiated a way of thinking about people that could be dehumanizing, that could reduce rich individual lives to points on a graph, deviations from a mean, errors around an ideal. The mathematics itself is neutral. The bell curve neither knows nor cares what it is describing. But the choice of what to measure, how to interpret the results, what policies to base on statistical findings, these are human choices, laden with values and assumptions. Quetelet believed he was practicing objective science, but he brought to his work all the assumptions of his time and place. Ideas about what was normal, what was desirable, what was worthy of measurement. Still, we must acknowledge what he achieved. Before Quetelet, statistics was primarily a tool of statecraft, counting population and resources for purposes of taxation and military recruitment. Quetelet helped transform it into a scientific discipline with broader applications. He showed that careful quantitative analysis could reveal truths not accessible to casual observation. He demonstrated that mathematics could extend beyond physics and astronomy to illuminate questions about society and humanity. As Quetelet aged, his work continued to influence new generations of thinkers. The social sciences were emerging as distinct disciplines, and they eagerly adopted statistical methods as a way of establishing their scientific credentials. Economists built mathematical models of markets and behavior. Sociologists analyzed patterns in social structure and change. Psychologists measured intelligence and personality. All were following paths that Quetelet had helped to open, applying mathematics to the study of human beings. When he died in 1874, Quetelet left behind a transformed landscape of knowledge. The marriage of mathematics and social observation that he had pioneered was now firmly established. Governments routinely collected statistical data. Sophie Germain, 1776 to 1831. Let us step back now to the turn of the 19th century, to revolutionary France, a nation in upheaval, where the old order was being torn down and new possibilities, and new dangers, were emerging daily. In Paris, amid the political tumult, a young girl sat reading in her father's library, discovering in the pages of a mathematics book a world more orderly and beautiful than the chaos outside her windows. Her name was Marie-Sophie Germain, and she would become one of the most gifted mathematicians of her age, making profound contributions to number theory and physics despite facing obstacles that would have discouraged almost anyone else. Sophie Germain was born in 1776 into a relatively prosperous merchant family. Her childhood coincided with the French Revolution, and she grew up hearing the sounds of distant riots, witnessing the fear and uncertainty that gripped Paris during the Terror. In these frightening times, the young Sophie found refuge in her father's library. There, at age 13, she discovered the story of Archimedes, the ancient Greek mathematician who had been so absorbed in a geometric problem that he didn't notice when soldiers entered his city, and who died still focused on his diagrams. This story captivated her. If mathematics could be so compelling that even death became secondary, she wanted to know what made it so powerful. She began teaching herself from the books in her father's library, works on mathematics and astronomy, some in Latin, which she also taught herself in order to read them. Picture her late at night, wrapped in blankets against the winter cold, candles burning low as she worked through Euler's treatises and Newton's Principia. Her parents were alarmed by this obsession. They believed that such intense intellectual work was inappropriate and even dangerous for a young woman. They tried to discourage her, taking away her candles and fire to prevent her from studying at night. But Sophie simply wrapped herself in quilts and worked by whatever light she could find, so determined to understand mathematics that physical discomfort meant nothing. Eventually her parents relented, recognizing that her passion could not be suppressed. But the larger world of mathematics remained closed to her. The École Polytechnique, France's premier institution for mathematical and scientific education, did not admit women. Sophie could not attend lectures, could not participate in discussions, could not submit work under her own name without facing dismissal or mockery. So she devised a strategy. She would use a man's name, would create a fictional identity that could move through the mathematical world freely while she remained hidden. She chose the name Monsieur Antoine-Auguste Leblanc, claiming to be a former student of the École Polytechnique. Under this pseudonym, she obtained lecture notes from courses and began submitting written work to professors. Her papers on analysis attracted the attention of Joseph-Louis Lagrange, one of the greatest mathematicians of the age. Impressed by the quality of her work, Lagrange asked to meet the talented Monsieur Leblanc. When Sophie was forced to reveal her true identity, Lagrange was astonished, and to his credit, he became her mentor and advocate, providing guidance and encouragement despite her gender. But Lagrange's support could only go so far. The mathematical establishment remained closed to women. Sophie could not publish easily under her own name, could not present papers to academies, could not hold academic positions. She worked alone, in her rooms in Paris, corresponding with mathematicians across Europe, but unable to participate fully in the mathematical community. Every result she obtained in isolation. Every proof she constructed without the benefit of regular discussion and collaboration. Yet despite these obstacles, her work in both number theory and mathematical physics would prove to be of lasting importance. Imagine Sophie in her study on a quiet morning, sunlight streaming through tall windows onto a desk covered with papers. She is working on what would become known as Fermat's last theorem, one of the most famous unsolved problems in mathematics. Fermat had claimed that the equation x to the power of n plus y to the power of n equals z to the power of n has no whole number solutions when n is greater than 2, but he had left no proof. For over a century, mathematicians had struggled with this problem, making progress in special cases, but unable to achieve a general proof. Sophie approached the problem with remarkable creativity. She developed a special case that became known as Sophie-Germain's theorem, showing that for certain prime numbers, now called Sophie-Germain primes, the first case of Fermat's last theorem must hold. Her approach involved intricate arguments about the divisibility properties of numbers, requiring both technical skill and deep insight into the structure of arithmetic. Though she could not solve Fermat's last theorem completely, it would remain unsolved until 1995. Her contribution represented significant progress and demonstrated techniques that later mathematicians would build upon. But her work in number theory, brilliant as it was, might have remained unknown if not for her correspondence with Carl Friedrich Gauss, perhaps the greatest mathematician of the 19th century. Sophie wrote to Gauss under her pseudonym, sharing her results in number theory. Gauss responded enthusiastically, recognizing in Monsieur Leblanc a kindred spirit, someone who shared his passion for the intricate patterns hidden in the properties of whole numbers. Their correspondence continued for years, with Sophie eventually revealing her true identity. The revelation came about in an unexpected way. During the Napoleonic Wars, when French troops occupied the German city of Brunswick, where Gauss lived, Sophie used her family's connections to ensure that the famous mathematician would not be harmed. When Gauss learned that his protector was actually his correspondent, Monsieur Leblanc, he wrote to her with admiration and astonishment. He praised not just her mathematical ability, but her courage and determination in pursuing mathematics despite the barriers she faced. Yet even Gauss's admiration could not fully open the doors of the mathematical world to Sophie. She turned her attention to a problem in mathematical physics, explaining the patterns that emerge when a thin elastic plate vibrates. This was not merely a theoretical question. Understanding the vibrations of elastic surfaces had practical applications in engineering and acoustics. The French Academy of Sciences announced a prize for whoever could provide a mathematical theory of elastic surfaces, complete with experimental verification. Picture Sophie conducting experiments in her rooms, perhaps using sand sprinkled on metal plates, striking the plates to make them vibrate, and watching as the sand settles into beautiful geometric patterns. The nodal lines where the plate doesn't vibrate. These patterns, discovered earlier by the physicist Ernst Chladni, were mesmerizing in their complexity and regularity. Sophie set herself the task of deriving the mathematical equations that would predict these patterns from first principles. This required her to venture into unfamiliar territory. She had to learn about elasticity theory, about partial differential equations, about the calculus of variations. She worked largely alone, without access to the informal discussions and collaborative work that helped other mathematicians tackle difficult problems. Her first attempts were flawed, and the Academy's judges rejected her initial submissions. But she persisted, refining her approach, teaching herself new mathematical techniques, conducting more experiments. On her third attempt, she produced a theory that was substantially correct, deriving a differential equation, now called the Germain equation, that described the vibrations of elastic plates. The Academy awarded her the prize in 1816, though even this recognition came with reservations and condescension. Some judges questioned whether a woman could really have understood the mathematics involved. Others suggested her work was not entirely original. The ceremony itself was awkward. Sophie, uncomfortable with public attention and perhaps aware of the skepticism she faced, did not attend. But the work stood on its own merits. The Germain equation became a foundation for the mathematical theory of elasticity, used by engineers and physicists throughout the 19th century and beyond. Sophie had created something lasting, a piece of mathematics that bore her name and her insight, a contribution that could not be erased or attributed to someone else. In her later years, Sophie continued to work on mathematics, though she never received an official position or steady recognition. She corresponded with fellow mathematicians, refined her number theory results, and thought deeply about the philosophy of mathematics and science. She was curious about whether there might be some general principles underlying all mathematical knowledge, some unifying framework that connected different branches of the discipline. These philosophical investigations, preserved in her manuscripts, show a mind always reaching for deeper understanding, never content with isolated results, but always seeking connections and foundations. There is a poignancy to Sophie Germain's story that we cannot ignore. Here was a mind of exceptional power and creativity, capable of contributions that any mathematician would be proud of, yet forced to work in isolation, to hide her identity, to fight for every small recognition. How much more might she have achieved in a world that welcomed her talents? What collaborations might have flourished if she could have worked openly with Lagrange, with Gauss, with Fourier, and the other great mathematicians of her time? Picture her in her final years, weakened by the cancer that would eventually take her life, still working on mathematics when her health permitted. She had never married, had devoted her life to intellectual pursuits that brought her satisfaction, but also isolation. Shortly before her death in 1831, Gauss arranged for the University of Göttingen to award her an honorary doctorate, a recognition of her mathematical achievements. But she died before the degree could be formally conferred, and even in death, official recognition proved elusive. Her death certificate listed her as rentier, property holder, rather than mathematician or scientist. Yet her legacy endures in ways both tangible and intangible. The Sophie Germain primes she identified continue to interest number theorists. The Germain equation remains a standard tool in engineering. But perhaps more importantly, her example inspired later generations of women who sought to enter mathematics and science. She proved that brilliance could overcome barriers, even if it could not entirely break them down. She demonstrated that passion and determination could sustain years of isolated work in pursuit of understanding. There is something profoundly human in Sophie Germain's story. The struggle against unjust limitations, the persistence in the face of discouragement, the satisfaction of solving a difficult problem despite all obstacles. She reminds us that mathematics is not a disembodied pursuit, but a human activity, shaped by the social context in which it occurs. The theorems may be timeless, but the process of discovering them is thoroughly embedded in history, influenced by who has access to education, who is allowed to publish, who receives encouragement and support. When we think of Sophie Germain late at night in her Paris study, working through a difficult proof, we should remember both her isolation and her connection. Isolated from the institutions and communities that might have nurtured her talent, but connected through correspondence to a wider world of mathematical minds who recognized her ability. She was alone but not entirely alone, excluded but not entirely excluded. She inhabited an in-between space, and from that difficult position, she created work of lasting value. As sleep approaches, hold this image. Sophie by candlelight, a page of calculations before her, the world outside dark and quiet. She has been working on a problem for hours, and suddenly she sees it. The pattern that makes everything clear, the insight that unlocks the proof. For a moment, nothing else exists but this understanding, this beautiful structure of logical necessity. The obstacles and injustices fade away, and there is only the mathematics, pure and perfect and true. This moment of clarity, this joy of understanding, this is what sustained her through all the difficulties. And in this we see mathematics at its most essentially human. Not the cold logic of textbooks, but the passionate pursuit of truth, the yearning to understand, the satisfaction of seeing clearly what was previously obscure. In Sophie Germain's quiet persistence, we find an image of intellectual courage, of brilliance refusing to be suppressed, of the human mind reaching always toward light. William Kingdon Clifford, 1845 to 1879. We move now to Victorian England, to an age of industrial progress and scientific optimism, when railways were connecting distant cities, when telegraph wires were spanning continents, when Darwin's ideas about evolution were transforming how humanity understood its place in nature. It was a time when mathematics and physics were being unified in powerful new ways, when abstract geometric thinking was beginning to reveal profound truths about the physical universe. In this intellectual climate, there lived a mathematician whose vision was so far ahead of his time that some of his deepest insights would not be fully appreciated until Einstein's theory of general relativity emerged nearly half a century after his death. His name was William Kingdon Clifford, and though he would die tragically young at 33, he packed into his brief career a remarkable range of achievements. In geometry, in algebra, in the philosophy of science, and in visionary speculation about the nature of space, time, and matter. He was a man of extraordinary energy and enthusiasm, combining rigorous mathematical thinking with a gift for communication that made complex ideas accessible to broader audiences. He lectured, he wrote, he debated. He thought deeply about the relationship between mathematics and physical reality, and he glimpsed connections that would only become clear generations later. Clifford was born in 1845 in Exeter, England, showing mathematical talent from an early age. He excelled at King's College London, and then at Trinity College, Cambridge, where he became second wrangler in the mathematical tripos, the second highest scorer in the prestigious and grueling examination that tested the very best mathematical minds in Britain. At Cambridge, he fell under the influence of the new geometric ideas that were revolutionizing mathematics in the mid-19th century. For 2,000 years, geometry had meant Euclidean geometry, the study of the flat space described in Euclid's Elements, where parallel lines never meet, where the angles of a triangle sum to exactly 180 degrees, where space is uniform and unchanging. But in the 19th century, mathematicians had begun to explore non-Euclidean geometries, strange new spaces where the familiar rules no longer held. On the surface of a sphere, for instance, what we call straight lines are actually great circles, and triangles have angles that sum to more than 180 degrees. Mathematicians like Lobachevsky, Boullier, and Gauss had shown that consistent geometries could be constructed where parallel lines do meet, or where infinitely many parallels can be drawn through a point. Picture young Clifford encountering these ideas for the first time, perhaps in a Cambridge lecture hall on a grey afternoon, rain pattering against tall windows. The lecturer is explaining how Riemann had generalized these ideas, showing that one could imagine spaces of any number of dimensions, with curvature that varied from point to point. Such spaces might be intrinsically curved, possessing geometric properties that depended not on their embedding in some higher dimensional space, but on internal measurements that inhabitants of the space could make. For Clifford, this was a revelation. If geometry was not unique, if multiple consistent geometries were possible, then which geometry described the physical space we actually inhabit? The question seemed almost metaphysical, but Clifford believed it was ultimately empirical, something that could be determined by careful measurement and observation. And he began to develop an even more radical idea. Perhaps the geometry of space itself was not fixed and uniform, but variable, perhaps even dynamic, changing in response to the presence of matter and energy. In 1870, Clifford wrote words that would prove prophetic. I hold in fact, 1. That small portions of space are in fact of a nature analogous to little hills on a surface which is on the average flat, namely, that the ordinary laws of geometry are not valid in them. 2. That this property of being curved or distorted is continually being passed on from one portion of space to another after the manner of a wave. 3. That this variation of the curvature of space is what really happens in that phenomenon which we call the motion of matter. Read these words slowly and consider their implications. Clifford is suggesting, in 1870, that space itself has structure, that it can be curved, that this curvature can propagate as waves, and that matter itself might be nothing but a manifestation of geometric properties of space. This is an astonishing anticipation of Einstein's general relativity, which would show in 1915 that gravity is indeed the curvature of space-time, that massive objects curve the space around them, and that this curvature affects how other objects move. Clifford glimpsed this truth nearly half a century early, using only geometric intuition and mathematical reasoning. But in 1870, there was no evidence for such ideas and no mathematical framework developed enough to make them precise. Einstein would need the tensor calculus developed by Ricci and Levi Civita, would need the physical insights from special relativity, would need years of difficult work to turn Clifford's vision into a rigorous physical theory. Clifford had the insight, but not the tools to fully develop it. His ideas were speculations, brilliant and suggestive, but not yet science in the sense of testable, quantitative predictions. Still, Clifford was far from idle. He made substantial contributions to algebra, developing what are now called Clifford algebras, mathematical structures that generalize complex numbers and quaternions. Imagine sitting with Clifford in his study at University College London, where he held a professorship, as he explains these ideas. He is animated, his hands moving as he describes how you can extend the familiar arithmetic of real numbers to systems where multiplication is not commutative, where the order of factors matters. These algebras, he shows, have deep connections to geometry, providing natural ways to represent rotations and reflections in spaces of any dimension. What Clifford discovered was that these algebraic structures, which seemed at first like pure abstractions, games mathematicians play with symbols, actually had profound geometric meaning. They could be used to describe the symmetries of space, to represent transformations elegantly and efficiently. More than a century later, Clifford algebras would find applications in physics, in representing the spin of elementary particles, in formulating laws of quantum mechanics and relativity in particularly beautiful ways. Once again, Clifford's pure mathematical work would prove to have physical significance that he could scarcely have imagined. He was also a gifted lecturer and popularizer of science. He gave public lectures at the Royal Institution, explaining mathematical and scientific ideas to general audiences with clarity and enthusiasm. He wrote essays on the philosophy of science, arguing for an empirical approach to knowledge, for the importance of evidence and reason over authority and tradition. His essay, The Ethics of Belief, remains a classic of philosophy, arguing that we have a moral responsibility to proportion our beliefs to the evidence, not to believe things simply because we find them comforting or traditional. Picture Clifford on a lecture platform, perhaps at the Royal Institution on Albemarle Street in London, the same venue where Faraday had demonstrated electromagnetic induction, and where so many great scientists had communicated their discoveries to the public. The lecture hall is full, gas lamps casting warm light, an audience of educated Victorians eager to hear about the latest developments in science and mathematics. Clifford is explaining non-Euclidean geometry, using models and diagrams, helping his listeners understand that the geometry of the universe is not a matter of logical necessity, but of empirical discovery. He was passionate about education, believing that mathematical thinking should be accessible to all who were willing to engage with it seriously. He worked on textbooks, on improving mathematical pedagogy, on showing that abstract ideas could be explained clearly without sacrificing rigor. In this, he was continuing a tradition we have seen throughout our journey: the commitment to transmission and teaching, the belief that knowledge is not truly possessed until it can be shared. But Clifford's life was shadowed by illness. He suffered from tuberculosis, the disease that had killed so many in the 19th century, that seemed almost epidemic among the intellectual class who worked long hours in poorly ventilated rooms. He pushed himself hard, lecturing, researching, writing, perhaps sensing that his time was limited. In 1878, his health deteriorated seriously, and he was forced to take leave from his professorship to seek better climate in warmer regions. Imagine Clifford in Madeira, the Portuguese island where he went hoping the mild climate might restore his health. He sits in a garden overlooking the Atlantic, the air warm and fragrant with flowers, trying to rest but unable to stop his mind from working through mathematical problems. He corresponds with colleagues back in England, continues to write when his strength permits. But the disease is relentless, and in March 1879, at the age of 33, William Kingdon Clifford died, far from home, his most visionary ideas still unproven and largely unrecognized. His death was mourned by the scientific community, which recognized it had lost a brilliant mind. But the full scope of his achievement would only become clear much later, when Einstein developed general relativity and showed that space-time is indeed curved by matter, that gravitational effects are geometric in nature. Physicists remembered Clifford's prophetic words. When quantum mechanics revealed the importance of spin, and Clifford algebras proved to be the natural mathematical language for describing it, mathematicians rediscovered his algebraic work. Clifford had seen correctly, but the world had needed decades to catch up. There is something particularly poignant about a vision so accurate, yet so premature. Clifford understood that geometry was not just a branch of pure mathematics, but the very language of physical reality. He grasped that space itself might have properties, might be shaped by the matter it contains, might be something dynamic rather than a passive stage on which physical processes unfold. These insights were correct, but he lacked the experimental evidence and mathematical machinery to develop them fully. Consider the nature of mathematical intuition that Clifford exemplified. He was not working from experimental data. No one in 1870 had measured the curvature of space or detected gravitational waves. He was reasoning purely from mathematical possibility, asking, if geometry can be non-Euclidean, if space can be curved, what would that mean for physics? This kind of thinking, exploring the physical implications of mathematical structures, would become increasingly important in 20th century physics, but Clifford was among its early pioneers. In his brief career, Clifford also contributed to other areas. He worked on graph theory, on the topology of surfaces, on the classification of geometric structures. He was interested in how transformations could connect different geometric spaces, in what properties remained invariant under various operations. This concern with invariance and transformation would become central to modern mathematics and physics, but in Clifford's time it was still emerging as a coherent approach. His students and colleagues remembered him as someone who combined intellectual brilliance with genuine warmth and enthusiasm. He didn't hoard his ideas or work in isolation, but shared them generously, engaged in discussions, welcomed questions and challenges. He saw mathematics as a collective endeavor, even when his own contributions were highly individual and original. As night deepens and sleep draws closer, let yourself imagine Clifford in his garden in Madeira, the sun setting over the Atlantic, painting the sky in shades of orange and gold. He is thinking about space, about curvature, about how geometry might be the key to understanding the universe. He cannot know that his vision will be vindicated, that future generations will recognize him as someone who saw truly, who glimpsed the geometric nature of reality before physics had caught up with mathematics. There is a melancholy beauty in this image, but also a kind of triumph. Clifford's ideas survived him, preserved in his writings, waiting for the moment when the world would be ready to understand them fully. He was unsung in the sense that he died before his deepest insights could be proven, before their importance could be fully recognized. But his vision endured, and eventually found its vindication in the work of Einstein and others who would show that yes, space is curved, yes, geometry is the language of gravity, yes, the structure of the universe is fundamentally mathematical in ways Clifford had intuited. In this we find comfort, that true insight, even when it arrives too early, even when it cannot be immediately developed or proven, can still survive, can still influence future thought, can still contribute to the slow accumulation of human understanding. Clifford's geometric vision, sketched in words and developed in algebras, became part of the foundation on which 20th century physics would be built. The mathematician himself may have been unsung, but his song, the idea that geometry is reality, continues to echo through modern science, as true now as when he first conceived it on a Victorian afternoon, looking at space not as Newton's absolute container, but as something living, curved, dynamic, and fundamentally mathematical. Émile Borel, 1871 to 1956. We arrive now at the threshold of the 20th century, an era when mathematics was becoming increasingly abstract, when the foundations of the discipline were being examined with new rigor, when old intuitions were being formalized with unprecedented precision. In this climate of mathematical renewal, a French mathematician would tackle one of the oldest and most puzzling aspects of reality, chance itself. How do we make randomness precise? How can we speak rigorously about probability when dealing with infinite possibilities? How do we measure the unmeasurable? These questions, which had troubled mathematicians and philosophers for centuries, would find their answers in the work of Émile Borel, whose contributions to probability and measure theory would provide the mathematical foundations for much of modern science. Émile Borel was born in 1871 in the small village of Saint-Affrique in southern France, the son of a Protestant minister. He showed exceptional mathematical talent from childhood, and by his late teens he had moved to Paris to study at the École Normale Supérieure, that crucible of French mathematical genius. There he absorbed the mathematical culture of late 19th century France, where rigor and abstraction were prized, where the great tradition of French analysis, Fourier, Cauchy, Galois, still shaped how mathematics was practiced. As a young mathematician, Borel became interested in questions about the foundations of mathematical analysis. What does it mean to say that a function is integrable? How do we assign sizes or measures to sets of points? These might seem like technical questions, but they touch on something fundamental. How do we extend our intuitive notions of length, area, and volume to sets that are infinitely complex, to situations where our geometric intuition breaks down? Picture Borel in his study at the École Normale in the 1890s, working through these problems with characteristic clarity and precision. On his desk are papers covered with symbols and careful logical arguments. He is thinking about sets of real numbers, collections of points on the number line. Some sets are simple. An interval from 0 to 1, for instance, clearly has length 1. But what about more complicated sets? What about the set of rational numbers between 0 and 1? The fractions, which are dense on the line, between any 2 points you can always find another rational, but somehow sparse. Most numbers are irrational. What length should we assign to this set? Borel's great insight was to develop what we now call Borel sets and Borel measures, a rigorous way of assigning sizes to even very complicated collections of points. He showed how to build up a systematic theory, starting with simple intervals, and then extending to more complex sets through operations of union, intersection, and complementation. The key was to work with countably infinite operations. You could take the union of infinitely many sets, as long as you could list them one by one, first, second, third, and so on. This might seem abstract, but it had profound implications for probability theory. When we flip a coin infinitely many times, or pick a random number between 0 and 1, we're dealing with infinite sample spaces, infinitely many possible outcomes. Classical probability theory, developed for finite collections of equally likely outcomes, didn't have the tools to handle such situations rigorously. Borel's measure theory provided those tools, giving mathematicians a precise way to talk about the probability of events in infinite sample spaces. Imagine Borel thinking about what it means to pick a random number between 0 and 1. Every specific number has probability 0 of being chosen. There are uncountably many possibilities, and singling out any one of them is infinitely unlikely. Yet we must pick some number, so something with probability 0 must occur. This seems paradoxical until you realize that what matters for probability is not individual points, but sets of points. The probability that your random number falls in the interval from 0.3 to 0.7, for instance, is 0.4, 40%. Borel's measure theory made such statements precise and rigorous. In 1909, Borel published a paper that introduced what would become known as the strong law of large numbers, a fundamental result about the long-run behavior of random processes. The law says, roughly, that if you repeat an experiment many times, the average of your results will almost surely converge to the expected value. Almost surely, this technical term, which Borel helped make precise, means with probability 1, though not with absolute certainty. It's a subtle distinction that measure theory allows us to articulate clearly. But Borel's interests extended far beyond pure mathematics. He was deeply engaged with how probability theory could be applied to real-world problems, to physics, to economics, to decision-making under uncertainty. He wrote about games of chance, analyzing optimal strategies in card games and other gambling scenarios. In doing so, he anticipated ideas that would later be developed more fully in game theory, the mathematical study of strategic interaction. Picture Borel sitting in a Parisian café in the 1920s, perhaps discussing probability with colleagues over coffee. The conversation might range from the most abstract questions about measure theory to practical questions about insurance, risk assessment, or the stock market. For Borel, there was no sharp divide between pure and applied mathematics. Both were aspects of the same endeavor to understand and quantify uncertainty. He was also one of the first mathematicians to think seriously about what we would now call game theory. In the 1920s, he wrote papers about two-person zero-sum games, situations where one person's gain is another's loss, and asked whether such games always have optimal strategies. He couldn't fully solve this problem, but he posed it clearly and explored special cases. The complete answer would come from John von Neumann in 1928, who proved the minimax theorem, but Borel had identified the key questions and shown why they mattered. During World War I, Borel served France in various capacities, including research on sound ranging, using the sound of artillery to locate enemy positions. This was an early application of probability and statistics to military problems, requiring sophisticated mathematical analysis of noisy data. After the war, he entered politics, serving in the Chamber of Deputies, and even briefly as Minister of the Navy. He was unusual among mathematicians in his ability to move between abstract theory and practical affairs, between the lecture hall and the legislative chamber. Yet despite these public activities, Borel continued his mathematical research throughout his life. In the 1920s and 30s, he worked on complex analysis, on the theory of functions, on continuing to develop and refine measure theory. He founded a journal, wrote textbooks, mentored students who would themselves become distinguished mathematicians. He was building institutions, creating frameworks that would allow mathematics to flourish in France through the turbulent 20th century. Imagine Borel in his later years, perhaps in the 1940s, reflecting on how probability theory had developed since his early work. The theory he had helped create was now being applied to quantum mechanics, where probability is fundamental to how we understand the behavior of subatomic particles. It was being used in statistical mechanics to understand the behavior of gases and other systems with enormous numbers of particles. It was becoming essential to information theory, to economics, to any field that dealt with uncertainty and randomness. He might have felt satisfaction seeing these applications, but also perhaps some concern. Borel was always aware that mathematical models were abstractions, that real-world situations were messier than idealized theories. He wrote thoughtfully about the limits of probability theory, about when it could be applied meaningfully and when it could mislead. He understood that giving mathematical form to uncertainty was powerful, but also carried responsibilities. The responsibility to understand what the mathematics really said and what it didn't, to avoid spurious precision, to recognize that some aspects of reality resist quantification. One of Borel's most famous contributions to popular understanding was the infinite monkey theorem. The idea that a monkey randomly typing on a typewriter for infinite time would almost surely eventually type any given text, including the complete works of Shakespeare. Borel used this thought experiment to illustrate ideas about probability and infinity, but also to make a point about practical impossibility. Yes, the monkey would eventually type Hamlet, but the expected time for this to happen is so vastly long that calling it possible, in any meaningful sense, is misleading. Some things are theoretically possible, but practically impossible, and this distinction matters. This insight connects to something deeper in Borel's thinking: his concern with making mathematics relevant to human understanding and decision-making. Abstract mathematics could deal comfortably with infinities, with events of probability zero that nonetheless might occur, with processes extending forever. But human life is finite. Practical decisions must be made with limited information and limited time, and a probability of 1 in 10 to the 100th power is, for all practical purposes, indistinguishable from zero. In his office at the Sorbonne, where he taught for many years, Borel might explain these ideas to students with patient clarity. Mathematics, he would emphasize, gives us powerful tools for thinking about uncertainty, but we must always keep in mind what the tools can and cannot do. Measure theory allows us to assign probabilities rigorously, to handle infinite sample spaces, to prove theorems about limiting behavior. But applying these tools to real situations requires judgment, requires understanding the assumptions built into the models, requires recognizing the difference between mathematical idealization and messy reality. During World War II, now in his 70s, Borel continued working despite the German occupation of France. He protected Jewish colleagues, maintained the mathematical community as best he could through difficult times, continued to think and write about mathematics even as the world around him was consumed by war. There is something admirable in this persistence, this commitment to intellectual work even in the midst of catastrophe, a reminder that mathematics is one of the permanent human endeavors, continuing through all upheavals. After the war, Borel lived long enough to see the early development of computers and to recognize their potential importance for probability and statistics. The ability to generate pseudo-random numbers, to simulate random processes, to perform calculations that would have been impossibly tedious by hand. All of this would transform how probability theory could be applied. Borel, who had spent his career developing the theoretical foundations, could glimpse how these foundations would support a vast edifice of practical applications. When he died in 1956 at the age of 84, Borel left behind a transformed mathematical landscape. The measure theory he had pioneered was now fundamental to analysis, probability, and many areas of pure and applied mathematics. His work on games anticipated developments that would shape economics and political science. His writings on the interpretation and application of probability had set a standard for thoughtful engagement with the relationship between mathematics and reality. Yet his name is not widely known outside mathematics. When people use probabilistic reasoning, when economists build models of markets under uncertainty, when machine learning algorithms are trained on data, when physicists describe quantum phenomena, in all these applications of probability theory, they are using frameworks that Borel helped create. But the frameworks have become so standard, so embedded in how we think, that their origins are forgotten. Borel is unsung in the sense that his contributions have been absorbed so thoroughly into mathematics and its applications that they seem almost obvious in retrospect. But there was nothing obvious about creating a rigorous theory of measure and probability. It required seeing clearly what earlier mathematicians had left vague, identifying precisely where intuition failed and formalization was needed, building systematic frameworks that could handle the infinite and the infinitesimal with equal rigor. This was Borel's achievement, not a single dramatic theorem that bears his name in popular consciousness, but a patient construction of foundations that made an entire edifice of subsequent mathematics possible. As you drift deeper into rest, imagine Borel in a quiet moment, perhaps walking through the Luxembourg Gardens near the Sorbonne on a peaceful afternoon. The gardens are green, the fountains playing, students strolling and discussing ideas. Borel is thinking about probability, about how to capture mathematically the notion of almost surely, about how infinite sequences of random events behave in the limit. These are abstract thoughts, but they connect to everything, to the reliability of measurements in physics, to the fairness of games, to how we make decisions when outcomes are uncertain. There is something peaceful in this image of mathematical thought as a kind of contemplation, a patient working through of difficult ideas not for fame or recognition, but for the satisfaction of understanding. Borel spent a long life doing this work, building theories that would outlast him, creating tools that would enable discoveries he could not foresee. In his careful formulations about measure and probability, we find mathematics at its most rigorous and most useful, providing precise language for concepts that had previously been handled only intuitively, giving us the power to reason about chance with the same clarity we bring to geometry or arithmetic. This is the gift Borel gave, the gift of precision about uncertainty, of rigor about randomness, of making the unmeasurable measurable through patient, careful thought. Srinivasa Ramanujan, 1887 to 1920. Our journey takes us now to a very different landscape, to southern India at the turn of the 20th century, to the temple town of Kumbakonam in Tamil Nadu, where ancient traditions of learning coexisted with the institutions of British colonial rule. Here, in circumstances far removed from the great mathematical centers of Europe, a young man with almost no formal training would produce mathematics of such depth and originality that it would astonish the mathematical world and continue to yield new insights more than a century after his death. His name was Srinivasa Ramanujan, and his story is unlike any other in the history of mathematics. A story of pure intuition colliding with formal rigor, of genius emerging from isolation, of collaboration across vast cultural and intellectual distances. Ramanujan was born in 1887 into a Brahmin family of modest means. His father worked as a clerk in a cloth merchant's shop. His mother was a strong-willed woman who sang devotional songs at the local temple. The family was not wealthy, but they valued education and ensured that young Ramanujan attended school. From his earliest years, he showed an extraordinary gift for mathematics, memorizing formulas and solving problems with an ease that amazed his teachers. By age 11, he had mastered books meant for college students. By 13, he was discovering results in trigonometry on his own, results that had taken European mathematicians centuries to develop. But the path ahead was not smooth. At 15, Ramanujan obtained a copy of a book that would change his life. G.S. Carr's synopsis of elementary results in pure and applied mathematics. This was not a textbook in the ordinary sense, but a compendium of thousands of formulas and theorems, mostly stated without proof. For a conventional student, such a book might have been overwhelming or frustrating. But for Ramanujan, it was a revelation. Here were patterns, relationships, structures, and no explanations of how they had been discovered. He set himself to rediscovering the proofs, to understanding why these formulas were true, and in the process he began to see connections that went beyond what the book contained. Picture Ramanujan as a teenager, working on a slate in the dim light of his family's modest home. Paper was expensive, so he used chalk on slate, filling it with calculations, then wiping it clean to make room for more. The formulas flowed from his mind in profusion. Infinite series, continued fractions, integrals, identities connecting seemingly unrelated mathematical objects. He worked with an intensity that worried his family, often late into the night, absorbed in patterns and relationships that he perceived with an intuition that seemed almost mystical. But this very intensity created problems. When Ramanujan went to college, he focused so exclusively on mathematics that he neglected his other subjects and failed his examinations. He lost his scholarship and had to leave college. He tried again at another institution with the same result. Brilliant in mathematics, failing everything else, unable or unwilling to conform to the requirements of formal education. By his early 20s, he was married, unemployed, and without any official credentials, yet his notebooks were filling with mathematics that would have astounded professional mathematicians if they had known of it. Ramanujan's mathematics was unlike the European tradition in important ways. European mathematics, especially by the early 20th century, prized rigor and proof above all. A result was not truly established until every step had been justified, every assumption stated explicitly, every logical gap filled. But Ramanujan worked differently. He saw formulas as if they were revealed to him, perceived relationships with an intuitive certainty that made formal proof seem almost beside the point. He would write down astonishing identities, equations claiming that certain infinite sums or products had exact values, without showing how he had arrived at them. Consider one of his formulas for pi, the ratio of a circle's circumference to its diameter. Ramanujan discovered that 1 divided by pi equals a certain infinite series involving factorials and large numbers, a formula so unexpected and beautiful that when mathematicians first saw it, they could scarcely believe it was correct. Yet it was, and it became the basis for some of the fastest algorithms for computing pi to many decimal places. But Ramanujan provided no derivation, no explanation of how he had found this extraordinary relationship. It simply appeared in his notebooks, one gem among thousands. By 1913, Ramanujan had found a clerical position in the Madras Port Trust, which gave him some financial stability and, crucially, a supervisor who recognized his mathematical talent. This supervisor encouraged Ramanujan to write to prominent mathematicians in England, sharing his results and seeking recognition. Most of these letters were ignored or politely dismissed. The recipients could not make sense of the strange formulas from an unknown Indian clerk. But one letter reached G.H. Hardy at Cambridge University, and Hardy was astute enough to recognize what he was seeing. Imagine Hardy in his rooms at Trinity College, Cambridge, examining Ramanujan's letter with a mixture of bewilderment and growing excitement. Some of the formulas were already known. Some were trivially false. But others were breathtaking in their originality and depth. Hardy showed the letter to his collaborator J. Littlewood, and together they worked through the night, trying to understand what this unknown Indian mathematician had discovered. By morning, they had reached a conclusion. This was the work of genius, perhaps the greatest natural mathematical talent since the 18th century. Hardy wrote back to Ramanujan, encouraging him to come to Cambridge. This was not a simple proposition. Ramanujan was a Brahmin, and traditional Brahmin practice forbade ocean voyages. His mother initially opposed the idea strongly, but Ramanujan felt compelled to go, believing it was his destiny to share his mathematics with the world. In 1914, overcoming family objections and practical difficulties, he boarded a ship for England, leaving behind the tropical warmth of India for the cold, grey skies of Cambridge. Picture Ramanujan arriving in England, everything strange to him: the climate, the food, the social customs, the academic culture. He was a vegetarian in a country where vegetarian food was scarce and poorly understood. He was a deeply religious Hindu in a secular academic environment. He was a self-taught mathematician with gaps in his formal training, entering one of the world's most rigorous mathematical communities. The challenges were immense. Yet the collaboration between Ramanujan and Hardy would prove to be one of the most fruitful in mathematical history. Hardy provided what Ramanujan lacked: formal training in proof techniques, knowledge of what was already established in European mathematics, rigorous standards for verification. Ramanujan provided what Hardy lacked: an inexhaustible source of novel ideas, an intuitive grasp of patterns that formal methods alone would never have revealed, a way of seeing mathematics that was fresh and unconstrained by conventional approaches. They worked together on many problems, particularly in number theory and analysis. They studied the partition function, which counts how many ways a number can be expressed as a sum of positive integers. While earlier mathematicians had found approximate formulas for this function, Ramanujan discovered exact formulas involving complex analysis and infinite series. These formulas were so intricate and unexpected that they seemed almost magical, yet Hardy helped verify them rigorously, confirming that Ramanujan's intuition had led him to profound truths. In quieter moments, Hardy would marvel at Ramanujan's mind. How did he see these patterns? Where did these formulas come from? Ramanujan would sometimes say that the goddess Namagiri, the family deity, showed him the mathematics in his dreams. Hardy, an atheist and rationalist, didn't believe in divine revelation, but he recognized that Ramanujan's thought processes were fundamentally different from conventional mathematical reasoning. Ramanujan perceived relationships directly, holistically, in ways that defied easy explanation. But Ramanujan's time in England was difficult in ways beyond the intellectual. The climate was harsh for someone accustomed to southern India. The wartime rationing of World War I made it even harder to maintain his vegetarian diet. He struggled with illness, tuberculosis, vitamin deficiencies, perhaps other conditions that were never properly diagnosed. By 1917, he was seriously ill, spending time in sanatoria, his mathematical productivity declining as his health deteriorated. Even in illness, his mind continued to work. In what he must have suspected might be his final months, Ramanujan made what may be his most mysterious discovery, the Mach theta functions. These were mathematical objects that resembled certain well-understood functions, but behaved differently in crucial ways. Ramanujan wrote to Hardy about them in early 1920, providing examples and formulas, but little explanation of their properties or significance. He died a few months later, at age 32, having returned to India, where he hoped the climate might restore his health. For decades, the Mach theta functions remained enigmatic. Mathematicians recognized they were important, but couldn't fully understand them. Only in 2002, more than 80 years after Ramanujan's death, was a complete theory of Mach theta functions finally developed, showing that they were connected to deep areas of mathematics that hadn't even existed in Ramanujan's time, to quantum modular forms, to mathematical physics, to areas Ramanujan could not have imagined. Once again, his intuition had led him to objects of fundamental importance, but the full meaning of his discovery would only become clear long after his death. Ramanujan's notebooks, those slate-copied compilations of thousands of formulas, became objects of intense study. Mathematicians would spend careers working through them, verifying results, seeking proofs for claims Ramanujan had simply stated. Again and again, they found that he had been right, that his intuitive leaps had landed on solid ground, even when the path he had taken was invisible to others. Some of his results led to new areas of research, to connections between fields that seemed unrelated, to applications in physics and computer science that Ramanujan had not anticipated. Consider what Ramanujan's story tells us about the nature of mathematical discovery. The standard narrative emphasizes training, rigor, systematic development of ideas from established foundations. Ramanujan shows us something different, that mathematical insight can arise from pattern recognition, from intuitive leaps, from ways of thinking that don't follow conventional paths. Both approaches are valuable. Hardy needed Ramanujan's intuition to see possibilities he would never have imagined. Ramanujan needed Hardy's rigor to verify and communicate his discoveries to the mathematical world. But Ramanujan's story also highlights something troubling. How much talent might be lost because of barriers of class, geography, and opportunity. Ramanujan was extraordinarily fortunate in encountering people who recognized his gifts and helped him connect with the wider mathematical world. How many others with similar potential never get such opportunities? How many brilliant minds remain unknown because they lack access to education, to mentors, to communities where their talents can be recognized and developed? There is also something profound in the collaboration between Hardy and Ramanujan. Two men from vastly different backgrounds, cultures, and approaches to mathematics, finding common ground in their shared love of mathematical truth. Hardy was English, aristocratic in bearing, trained in the rigorous traditions of Cambridge. Ramanujan was Indian, from a modest background, self-taught through intuition and individual exploration. Yet they could communicate, could work together, could create mathematics that neither could have produced alone. This reminds us that mathematics is a universal language, transcending cultural boundaries, accessible to minds wherever they may be found. In his final years back in India, weakened by illness, Ramanujan must have reflected on his extraordinary journey, from the temple town of Kumbakonam to the ancient halls of Cambridge, from working in isolation on a slate to collaborating with Hardy at Trinity College, from being an unknown clerk to being elected a Fellow of the Royal Society, one of the highest honors in science. He had lived long enough to receive some recognition, but not long enough to see how far his influence would extend. As sleep draws very near, let yourself rest in the image of Ramanujan at work, perhaps in his Cambridge rooms on a rare sunny afternoon, or back in India under the warm southern sky, filling pages with formulas, following patterns that only he can see, trusting in an intuition that connects him to something deeper than formal logic alone can reach. There is mystery here, the mystery of how the human mind can perceive mathematical truth, how insight can arrive unbidden, how understanding can emerge from sources we cannot fully explain. In Ramanujan's brief, brilliant life, we see mathematics as both universal and culturally situated, both rigorous and intuitive, both collaborative and individual. We see genius flowering in unexpected places, overcoming obstacles, finding ways to contribute despite all barriers. And we see, ultimately, that mathematical truth welcomes all who seek it sincerely, regardless of their training or background, that the patterns underlying reality reveal themselves to those with eyes to see them, whether in Cambridge or Kumbakonam, through formal proof or intuitive leap. This is Ramanujan's enduring gift, not just the thousands of formulas he discovered, but the reminder that mathematics belongs to everyone, that insight can come from anywhere, that the human capacity for understanding is richer and more varied than any single tradition can encompass. Sofia Kovalevskaya, 1850 to 1891. We turn now to 19th century Russia, to a world of vast social change, where old certainties were being questioned and new possibilities were emerging, slowly and against resistance. It was an era when women across Europe were beginning to demand access to higher education, to professional opportunities, to the intellectual life from which they had been systematically excluded. In this context of gradual but incomplete progress, a Russian woman would become the first female mathematician to hold a university professorship in modern Europe, making groundbreaking contributions to analysis and mathematical physics, while navigating barriers that would have stopped almost anyone else. Her name was Sofia Kovalevskaya, and her story shows both how far determination and brilliance could carry someone, and how much energy had to be expended simply to gain access to opportunities that men received as a matter of course. Sofia Vasilievna Korvin-Krakovskaya was born in 1850 in Moscow into an aristocratic family. Her father was a general in the Imperial Russian Army, her mother from a family of German intellectuals. The household was cultured and educated, with books, music, and lively conversation, but like most families of the time, they did not imagine that their daughters would pursue serious intellectual careers. Yet from childhood, Sophia showed an intense curiosity about mathematics, a fascination with patterns and logical reasoning that seemed as natural to her as breathing. There is a famous story from her childhood that Sophia herself loved to tell. When the family moved to a new estate, they found themselves short of wallpaper for one of the rooms. As a temporary measure, they covered the walls with old papers from her father's library, papers that happened to be from his university days, including lecture notes on differential and integral calculus. Young Sophia spent hours in that room, studying the mysterious symbols on the walls, trying to understand what they meant. She would trace the formulas with her fingers, puzzling over the notation, beginning to perceive the logic underlying these strange expressions. When she later encountered calculus formally, she found she already had an intuitive grasp of the concepts from those childhood hours studying her wallpaper. As she grew older, Sophia's desire to study mathematics seriously intensified, but Russian universities did not admit women. Nor could she easily study abroad. Unmarried young women could not travel without their parents, and her father refused to allow her to go abroad for education he considered unnecessary. So Sophia and her sister devised a plan that was common among educated Russian women of the time: a marriage of convenience. Sophia married Vladimir Kovalevskaya, a young paleontologist who was also eager to study abroad. The marriage was initially platonic, a practical arrangement to give Sophia the independence to pursue her studies. In 1869, the newlyweds left Russia for Heidelberg, Germany. Picture Sophia arriving in this German university town, finally free to attend lectures, to immerse herself in mathematics. But even here, she faced obstacles. Women were not officially admitted to the university, so she had to obtain permission from individual professors to attend their lectures. Most granted it, impressed by her obvious seriousness and ability, but the situation remained precarious, dependent on individual goodwill rather than institutional right. After 2 years in Heidelberg, Sophia moved to Berlin, hoping to study with Karl Weierstrass, one of the greatest mathematical analysts of the 19th century. But the University of Berlin would not admit women to lectures under any circumstances. Weierstrass, however, recognized Sophia's extraordinary talent when he tested her mathematical knowledge. Though he could not officially teach her, he agreed to give her private lessons, meeting with her weekly to work through problems and discuss advanced topics in analysis. Imagine these lessons in Weierstrass's study: the elderly professor and the young Russian woman, working through complex problems in the theory of functions, discussing partial differential equations, exploring the frontiers of mathematical knowledge. Weierstrass would set her problems to work on between meetings, and Sophia would return with solutions that often surprised him with their elegance and insight. He came to regard her as one of his most talented students, writing later that she had the gift of intuitive genius. Under Weierstrass's guidance, Sophia produced 3 papers of such quality that the University of Göttingen agreed to award her a doctorate in mathematics, in absentia, without requiring her to attend the university or pass oral examinations, simply on the strength of the work itself. This was highly unusual, a recognition that her papers were of exceptional merit. One of these papers, on partial differential equations, contained what is now known as the Cauchy-Kovalevskaya theorem, a fundamental result about the existence of solutions to certain types of differential equations. The Cauchy-Kovalevskaya theorem addresses a question that might seem technical, but is actually central to much of mathematical physics. Given certain initial conditions, does a differential equation have a solution? And if so, is it unique? This question matters whenever we try to predict how a physical system will evolve. Whether we're modeling heat flow, fluid motion, electromagnetic fields, or countless other phenomena described by differential equations. Sophia's theorem provided precise conditions under which we can be certain that solutions exist and are determined uniquely by the initial data. Picture Sophia working on this theorem, perhaps in her rooms in Berlin, papers spread across a desk, working through the intricate analytical arguments required to establish her result. She is combining techniques from complex analysis with insights into the structure of partial differential equations, seeing connections that allow her to prove existence and uniqueness simultaneously. This is sophisticated mathematics, requiring both technical mastery and conceptual clarity. Yet she was only in her mid-20s, working largely in isolation, without the support of a research community or institution. With her doctorate in hand in 1874, Sophia might have expected to find an academic position, but none were available. Universities did not hire women, regardless of their qualifications. She returned to Russia with her husband, and for several years she stepped away from mathematics, trying to make a life in St. Petersburg. She and Vladimir started a publishing company, pursued various business ventures, had a daughter. The marriage, which had begun as a formality, had become real, but it was troubled. Vladimir's business dealings were increasingly questionable, and he fell into depression and financial difficulties. During these years away from mathematics, Sophia must have felt the loss acutely. She had trained with one of the world's greatest mathematicians, had produced work of genuine importance, had demonstrated abilities equal to any male mathematician of her generation. Yet she could find no position, no way to continue her research professionally. The talent that had been nurtured by Weierstrass was being wasted because institutions would not recognize it. Then, in 1883, Vladimir died by suicide, leaving Sophia emotionally devastated, but also free to reshape her life. With the support of Gösta Mittag-Leffler, a Swedish mathematician who had studied with Weierstrass and knew Sophia's abilities, she was offered a position at the newly established Stockholm University in Sweden. This was groundbreaking. Sophia became the first woman in modern Europe to hold a university professorship in mathematics. She was initially hired on a temporary basis and without salary, but it was a foothold, a chance to return to mathematics. Picture Sophia in Stockholm in 1884, lecturing to students, finally able to practice her vocation openly. She lectures in Swedish, a language she has learned rapidly out of necessity. Her courses attract students, her reputation grows. She begins publishing again, working on problems in mathematical physics and analysis. She is productive, energetic, making up for lost time. In 1888, she achieved perhaps her greatest triumph. The Paris Academy of Sciences announced a prize for work on the rotation of a rigid body around a fixed point, a classical problem in mechanics that had been studied for over a century. Sophia tackled this problem with characteristic brilliance, discovering a new integrable case that no one had found before. Her solution was so impressive that the Academy increased the prize money from 3,000 to 5,000 francs in recognition of its exceptional quality. The problem Sophia solved involved understanding how a spinning object, imagine a top or a gyroscope, behaves when one point is held fixed. This is described by complicated differential equations involving angular velocities and moments of inertia. Earlier mathematicians had found solutions for special cases, But Sophia discovered a completely new case where exact solutions were possible, one involving particular relationships between the body's moments of inertia and the position of its center of mass. This required not just technical skill but physical intuition, an ability to see which mathematical assumptions would lead to tractable equations. After this success, Stockholm University promoted Sophia to a full professorship with salary, making her position secure. She was elected to the Russian Academy of Sciences as a corresponding member, though even this came with resistance. Some members objected to admitting a woman. She continued her mathematical research, worked on a novel. She was also a talented writer, raised her daughter, and built a life that finally allowed her talents full expression. But this period of productivity and recognition was tragically brief. In early 1891, returning to Stockholm from a trip, Sophia caught a chill that developed into pneumonia. In those days before antibiotics, pneumonia was often fatal. She died on February 10, 1891, at age 41, at the height of her mathematical powers. Once again, we encounter the tragedy of a brilliant mathematician dying young, of work left undone, of potential unfulfilled. Yet Sofia Kovalevskaya accomplished more in her 41 years than most mathematicians accomplish in much longer lives. She proved that women could do mathematics at the highest level, breaking down barriers and creating openings for those who would follow. She made lasting contributions to analysis and mechanics, work that remains relevant and continues to be studied. She showed that talent could not be indefinitely suppressed by social conventions, that brilliance would eventually find expression even against enormous resistance. Consider what Sophia's life required of her. She had to leave her country to study, contract a marriage of convenience to gain independence, study privately because universities would not admit her, produce work so outstanding that degrees would be granted as exceptions, wait years for any professional opportunity, and continuously prove herself in ways male mathematicians never had to. The energy expended on simply gaining access to mathematics, on navigating these barriers, was extraordinary. What more might she have accomplished if these obstacles had not existed? Yet there is also inspiration in her persistence. She did not give up when faced with rejection, did not accept that her gender should determine her possibilities, kept working and learning even during the years when no professional future seemed possible. When opportunity finally came, she was ready, her skills honed, and her mind still engaged with mathematical problems. Her collaboration with Mittag-Leffler shows the importance of allies and advocates. Mittag-Leffler recognized Sophia's talent and worked to create an opportunity for her at Stockholm, taking professional risks to support her appointment. This reminds us that institutional change requires not just the persistence of those excluded, but also the willingness of those with power to open doors, to challenge conventions, to recognize that excellence can come from unexpected sources. In her writing and lectures, Sophia emphasized that mathematics was not a dry, mechanical discipline, but one requiring creativity and imagination. She saw connections between mathematical work and artistic creation, viewing both as expressions of human imagination constrained by their different forms of discipline, logical necessity in mathematics, aesthetic coherence in art. This perspective helped her communicate mathematical ideas to broader audiences, showing that technical work could be explained without sacrificing either rigor or beauty. As you rest now, nearly at sleep's edge, hold the image of Sophia in her study in Stockholm, working late into a winter evening. Outside, the northern darkness has fallen early, snow perhaps beginning to fall. Inside, lamplight illuminates the pages before her. Equations describing the motion of a rotating body, calculations working toward the result, that will win the Prix Borden from the Paris Academy. She is absorbed in the work, following the logic wherever it leads, using all the analytical tools Weierstrass taught her, adding her own insights and innovations. There is satisfaction in this scene. The satisfaction of finally being able to work openly, of having students and colleagues, of doing the mathematics she loves without having to justify her right to do so. The years of struggle have not been for nothing. She has proven what she always knew, that women could contribute to mathematics at the highest level, that talent transcends gender, that institutional barriers were arbitrary and unjust rather than natural and necessary. In Sofia Kovalevskaya's life and work, we see the beginning of a transformation, slow and incomplete but real. The doors she pushed open would make it easier for others to follow. The precedent she set would be invoked by later generations of women seeking access to mathematical education and careers. Her theorem bearing her name would continue to be taught, studied, and applied long after her death, a permanent contribution to mathematics independent of the biographical struggles that surrounded its creation. She was unsung in the sense that her achievements required extraordinary effort to accomplish what should have been ordinarily possible, that she had to be exceptional to receive what should have been accessible. But her voice, once finally heard, could not be silenced, and it echoes still through the lives of all who came after, who found the path slightly easier because she had walked it first. Benjamin Banneker, 1731 to 1806. Let us journey now across the Atlantic and back through time, to colonial America in the 18th century, to a land where the promise of liberty existed alongside the brutal reality of slavery, where Enlightenment ideals of reason and natural rights coexisted with systematic racial oppression. In this contradictory world, a free black man in rural Maryland would teach himself astronomy and mathematics, compile almanacs that were widely respected, contribute to the surveying of the new nation's capital, and challenge the founding fathers themselves about the inconsistency between their declared principles and their practices. His name was Benjamin Banneker, and his story shows us mathematics not as an abstract pursuit, but as a practical tool for understanding the world, and also as a means of asserting one's full humanity in a society that denied it. Benjamin Banneker was born in 1731 in Baltimore County, Maryland. His grandmother had been an indentured servant from England who, after gaining her freedom, had purchased enslaved workers to help run her tobacco farm. She eventually freed and married one of them, Banneker, who may have been of royal lineage from West Africa. Their daughter Mary married an enslaved man named Robert, whom she freed, and they took the name Bannaky or Banneker. Benjamin was born into this family as a free person, a status that was rare and precious in a society where the vast majority of people of African descent were enslaved. His early education came from his grandmother, who taught him to read using the Bible. For a brief period, he attended a small Quaker school where he learned basic arithmetic and reading. But his formal education was limited, perhaps 2 years at most, and after that he was largely self-taught, reading whatever books he could obtain, working on his family's tobacco farm, developing a reputation as someone who could solve difficult problems and fix mechanical devices. Picture young Banneker on the family farm in the 1750s, the rolling hills of Maryland spreading out around him, tobacco plants growing in careful rows. The work is hard, planting, tending, harvesting, but in the quiet moments, his mind turns to puzzles and problems. He is fascinated by how things work, by patterns and relationships, by the logic underlying mechanical systems and numerical relationships. When Banneker was in his early 20s, a traveling merchant showed him a pocket watch, a marvel of precision and craftsmanship. Banneker was captivated. He borrowed the watch, carefully took it apart, studied each component, made detailed drawings of every gear and spring. Then he returned the watch and set himself a challenge. Could he build a striking clock entirely from wood, using only the pocket watch as a model, scaling up the design to make a full-size timepiece? For months he worked on this project, carving gears from hardwood, calculating the ratios needed for the wheels and pinions, figuring out the escapement mechanism that would regulate the clock's movement. He had no training in horology, no books on clockmaking, just his observations of the pocket watch and his own mathematical reasoning. Yet he succeeded, creating a wooden clock that kept accurate time and chimed the hours. The clock became famous in the region, and it continued to work for decades, a testament to Banneker's mechanical aptitude and mathematical precision. Imagine that clock in Banneker's cabin, its wooden gears turning with patient regularity, marking the hours with wooden chimes. It represents something more than technical skill. It demonstrates a mind capable of understanding complex systems, of working from first principles, of achieving through self-education what others achieved through formal training. The clock was proof, visible to anyone who saw it, of Banneker's intellectual capabilities. For many years, Banneker lived quietly on his farm, tending his crops, reading when he could obtain books, observing the world around him with curiosity and care. But in 1788, when he was 57 years old, his life took a new direction. The Ellicott family, Quakers who ran a mill near Banneker's farm, befriended him and recognized his intellectual gifts. George Ellicott, a surveyor and amateur astronomer, lent Banneker books on astronomy and mathematics, along with instruments for making astronomical observations. Banneker seized this opportunity with remarkable energy. He taught himself astronomy from these books, working through the complex calculations required to predict the positions of celestial bodies, studying the mathematical models that described planetary motion. He began making his own observations with borrowed instruments, sitting up through the night to track the movements of stars and planets, recording data with meticulous care. Picture Banneker on a clear night in rural Maryland, the sky brilliantly dark in an era before electric lights, the Milky Way a luminous band across the heavens. He has set up a telescope on a makeshift mount, perhaps near his cabin. He is observing Jupiter, tracking its position against the background stars, noting the time of his observation with precision. Later, he will use these observations to calculate the planet's orbit, to verify the predictions in his astronomical tables, to deepen his understanding of celestial mechanics. What Banneker was doing required sophisticated mathematics, trigonometry for calculating positions on the celestial sphere, algebra for solving equations relating to planetary orbits, careful attention to the precision of measurements and the propagation of errors. He was working through the same material that students studied at universities, but he was doing it alone, in his 50s, with limited resources, driven by pure intellectual curiosity and determination. In 1791, Benjamin Banneker's mathematical skills led to a remarkable opportunity. Major Andrew Ellicott, George's cousin, was appointed to survey the boundaries of the new federal district that would become Washington, D.C. He asked Banneker to assist him in this important task. Banneker joined the survey team as an astronomical observer, responsible for operating the astronomical clock and the astronomical instruments used to establish the reference points for the survey. Surveying a 10-mile square tract required precise astronomical observations to establish latitude and longitude. Banneker's role was crucial. He made observations of stellar positions, calculated the local time from celestial measurements, maintained the astronomical instruments, and performed the complex calculations needed to establish the survey's geodetic framework. This was applied mathematics of the highest order, work that required both theoretical understanding and practical skill. Imagine Banneker at the survey camp, perhaps on a hill overlooking what would become the nation's capital. It is night, and he is making observations with the zenith sector, an instrument for measuring the positions of stars as they pass overhead. He records each observation carefully, knowing that errors here will propagate through all subsequent work. Later, by candlelight in his tent, he performs the calculations that will convert these raw observations into precise geographic positions. The irony was not lost on Banneker. Here he was, a black man helping to lay out a capital for a nation that enslaved hundreds of thousands of people who looked like him, including the brother and sister he himself would later be forced to sell to satisfy debts against the family farm. The contradiction between America's founding ideals and its practices was stark, and Banneker would directly address it. In August 1791, Banneker sent a letter to Thomas Jefferson, who was then Secretary of State. The letter was remarkable, respectful but unflinching. It challenged Jefferson on the contradiction between his declaration that all men are created equal and his ownership of enslaved people. Banneker included with the letter a manuscript of his astronomical calculations for an almanac he was preparing, as evidence of the intellectual capabilities of African Americans, as proof that the supposed inferiority used to justify slavery was a lie. Jefferson's reply was polite, but non-committal. He sent Banneker's almanac calculations to the Marquis de Condorcet at the French Academy of Sciences, but he did not substantively engage with Banneker's challenge about slavery. Still, the exchange became famous, published in pamphlets, cited by abolitionists as evidence against racist pseudoscience. Banneker had used his mathematical work not just as an intellectual achievement, but as a political and moral argument. From 1792 to 1797, Banneker published almanacs annually. These were practical documents, widely used by farmers, sailors, and surveyors. They contained astronomical tables showing the positions of the sun, moon, and planets throughout the year, predictions of eclipses, sunrise and sunset times for different latitudes, tide tables, and various other useful information. All of this required extensive calculation. Banneker performed thousands of mathematical operations to prepare each almanac, checking and rechecking his results to ensure accuracy. Picture Banneker working on an almanac in his cabin during the winter months. Papers are spread across his table, covered with columns of numbers. Positions of the moon calculated for each day of the coming year, eclipse predictions worked out months in advance, tide tables computed from lunar cycles. He works by firelight and candlelight, his aging eyes straining over the figures, but his mind still sharp, still capable of following complex calculations through many steps. The publication of these almanacs was significant beyond their practical utility. They demonstrated that a black man, self-taught, could produce work equal in quality to almanacs produced by white astronomers with university educations. They were tangible evidence against the ideology of racial inferiority, harder to dismiss than abstract arguments, because they existed as physical objects, used and valued by people who might not otherwise question racial hierarchies. Yet Banneker's later years were difficult. The almanacs ceased publication after 1797, perhaps because publishers lost interest, or because Banneker's aging made the intense calculation too taxing. He continued his astronomical observations and mathematical studies, but in relative obscurity. When he died in 1806, shortly after attending a neighbor's funeral, his papers and most of his possessions were destroyed in a fire that consumed his cabin the day of his burial. His wooden clock, that early triumph, was lost in the flames. Most of his manuscripts, his calculations, his journals, all were reduced to ash. What survived were the published almanacs, the memory of his work on the Washington Survey, and the letter to Jefferson. These fragments allow us to reconstruct something of his achievement, but we cannot know what else was lost in that fire. What other calculations, what observations, what thoughts about mathematics and astronomy that might have deepened our understanding of his intellectual life. Banneker's story reminds us that mathematics is not only an abstract discipline, but also a practical tool, essential to navigation, surveying, agriculture, and countless other human endeavors. The astronomical calculations in his almanacs helped farmers know when to plant, helped sailors navigate, helped surveyors establish property boundaries. This was mathematics in service to daily life, mathematics as a technology for understanding and managing the world. But his story also shows how mathematical achievement could serve as an argument for human dignity and equality. In a society that denied the intellectual capabilities of black people, Banneker's almanacs were proof of what many refused to see: that intellectual talent was not determined by race, that given opportunity and resources, people of all backgrounds could achieve at the highest levels. Consider how much harder Banneker's achievements were than those of his white contemporaries. He lacked formal education, had limited access to books and instruments, received no institutional support, and faced constant reminders that society did not expect or value intellectual work from someone who looked like him. Yet he taught himself astronomy, performed calculations that required years of practice to master, contributed to projects of national importance, and produced work that was recognized as excellent by those competent to judge it. As sleep approaches its deepest point, let the image of Banneker settle into your resting mind. Perhaps observing the stars from his Maryland farm on a clear autumn night, or bent over his calculations by candlelight, working through the mathematics that would predict the next lunar eclipse. There is peace in this image, the peace of someone absorbed in work that matters, work that connects him to the cosmos, to the predictable patterns underlying apparent chaos, to truths that transcend the injustices and limitations of his earthly situation. In Benjamin Banneker's quiet persistence, in his self-education and his achievements despite all barriers, we find another reminder that mathematical ability is universal, distributed across all populations, waiting only for opportunity to flourish. We see mathematics as both practical craft and intellectual achievement, both useful technology and profound understanding. And we see, once more, the tragedy of barriers, how much talent was lost to slavery and discrimination, how many potential Bannekers never had even the limited opportunities he found. His story is inspiring, but it should also make us ask, how many voices were silenced? How many brilliant minds were never allowed to develop? How much was lost to humanity because of systems that denied education and opportunity based on the accident of birth? In honoring Banneker, we honor not only what he achieved, but what he represents: the persistence of human intelligence and dignity, even in conditions designed to suppress them. Euphemia Lofton Haynes, 1890 to 1980. We come now to 20th century America, to Washington, D.C., the city that Banneker helped survey over a century earlier. The nation's capital in the early 1900s was a segregated city, divided by law and custom into separate and deeply unequal worlds for black and white residents. Schools were segregated, neighborhoods were segregated, opportunities were rigidly constrained by race. Yet even in this restrictive environment, there emerged a black woman who would become the first African-American woman to earn a doctorate in mathematics, and who would spend her long life fighting to expand educational opportunities and dismantle the structures of segregation. Her name was Euphemia Lofton Haynes, and her story shows us mathematics not as an escape from social reality, but as a tool for engaging with it, for building institutions, for demanding justice. Euphemia Lofton was born in Washington, D.C., in 1890, into a family that valued education intensely. Her father was a dentist and financier, one of the small but significant black professional class in the segregated capital. Her mother was a kindergarten teacher. The family understood that education was essential, both for individual advancement and for the collective progress of African Americans in a society that denied them equality. Young Euphemia attended the excellent but segregated M Street High School, later renamed Dunbar High School, which had an outstanding faculty and a tradition of academic excellence despite its underfunded facilities. Picture the young Euphemia in her high school mathematics classroom around 1905, working through problems in geometry and algebra. Her teachers are themselves exceptional. Many hold advanced degrees from northern universities, having come to Washington because segregation in other parts of the country made it impossible for them to use their education elsewhere. They recognize in Euphemia a quick mind, a facility with abstract reasoning, a determination to understand things deeply rather than superficially. After graduating from M Street High School, Euphemia attended Smith College in Massachusetts, one of the few institutions that would accept black students at the time, though even there she faced discrimination and isolation. She earned her bachelor's degree in mathematics in 1914, then returned to Washington to begin what would become a 6-decade career in education. She started teaching mathematics at Armstrong High School, one of Washington's segregated schools for black students. Teaching mathematics in a segregated school system in the early 20th century meant working with limited resources, outdated textbooks, overcrowded classrooms, and facilities that received a fraction of the funding given to white schools. Yet Euphemia approached this work with dedication and excellence. She was not merely teaching arithmetic and algebra. She was opening doors for her students, showing them that mathematics was accessible to them, that intellectual achievement was possible despite the barriers society placed in their way. Imagine Euphemia in her classroom in the 1920s, perhaps explaining the Pythagorean theorem to a room full of students. She draws a right triangle on the blackboard, constructs squares on each side, shows how the areas relate. But she is teaching more than geometry. She is teaching her students that they can understand difficult ideas, that their minds are capable of abstract reasoning, that the world's low expectations of them are wrong. In a segregated society that constantly told black students they were intellectually inferior, a black mathematics teacher demonstrating mathematical truth was performing an act of resistance. But Euphemia wanted to deepen her own mathematical knowledge. While teaching full-time, she pursued graduate education, earning a master's degree in mathematics from the University of Chicago in 1930. Then she continued to the doctorate, an almost unthinkable achievement for a black woman at that time. There were formidable obstacles: the need to balance full-time teaching with graduate study, the financial challenges of pursuing a doctorate without institutional support, the isolation of being perhaps the only black woman in her graduate program. She chose to work on a problem in finite groups, a branch of abstract algebra that had been pioneered by mathematicians like Galois and had become increasingly important in modern mathematics. Her dissertation, completed in 1943 at Catholic University of America, was titled Determination of Sets of Independent Conditions Characterizing Certain Special Cases of Symmetric Correspondences. It was technical, rigorous work in pure mathematics, demonstrating complete mastery of advanced algebraic concepts. Picture Euphemia working on her dissertation, perhaps late at night after a full day of teaching, papers spread across a desk in her home. She is working through abstract algebraic structures, proving theorems about the relationships between mathematical objects defined purely by their formal properties. This is mathematics at its most abstract, far removed from practical applications, pursued for the sake of understanding itself. Yet there is something profound in a black woman in segregated Washington mastering this material, claiming her place in a tradition that had historically excluded people who looked like her. When Euphemia Lofton Haynes received her doctorate in 1943, she became the first African-American woman to earn a PhD in mathematics. This was a milestone, breaking a barrier that had seemed almost insurmountable. Yet she did not pursue a research career at a university. Such positions were effectively closed to black women, regardless of their qualifications. Instead, she returned to what she had always done, teaching, now at the college level, and working to improve educational opportunities for black students in Washington. She taught at Minor Teachers College and later at the District of Columbia Teachers College, institutions that train teachers for the segregated school system. In teaching future teachers, she was multiplying her impact. Each teacher she prepared would go on to teach hundreds of students, spreading mathematical knowledge and demonstrating through their own competence what black educators could achieve. But Euphemia's work extended far beyond the classroom. She became deeply involved in educational policy and civil rights activism. She served on the District of Columbia Board of Education, where she fought against the inequalities of the segregated system and, after the Supreme Court's Browne versus Board of Education decision in 1954, worked to implement desegregation. She understood that mathematics and education were not separate from politics and justice, that the struggle for equality required engaging with institutions, challenging policies, and building alternative structures when existing ones were inadequate. Imagine Euphemia at a school board meeting in the 1950s or 60s, armed with statistics about funding disparities between white and black schools, with enrollment data showing overcrowding in black schools while white schools had empty classrooms, with achievement data demonstrating that when given equal resources, black students performed just as well as white students. She uses mathematics, statistics, data analysis, quantitative arguments, as a tool for social justice, showing through numbers what should have been obvious from principle, that the segregated system was unjust and harmful. She was also active in Catholic educational institutions and social service organizations, serving on boards, organizing programs, working to create opportunities for students who were excluded from mainstream institutions. She helped found or strengthen several schools and educational programs, understanding that structural change required building new institutions, not just reforming existing ones. In her teaching, Euphemia emphasized not just mathematical techniques but mathematical thinking, the ability to reason logically, to break complex problems into manageable parts, to persist when solutions were not immediately obvious. These were skills with application far beyond mathematics classrooms, skills that would serve her students well, whatever paths they took. She was preparing students to be doctors and teachers, yes, but also to be citizens capable of thinking critically, of analyzing arguments, of not accepting claims without evidence. Picture one of Euphemia's students, perhaps in the 1960s, sitting in her college mathematics class. The student might go on to teach mathematics in newly integrated schools, carrying forward the tradition of excellence that Euphemia embodied. Or the student might become an engineer, using mathematical skills to contribute to the space program or other technical fields that were just beginning to open to African Americans. Or the student might use the analytical skills learned in mathematics class to become a lawyer, a social worker, a policy analyst, applying mathematical thinking to social problems. Euphemia lived to see enormous changes in American society. Born in an era of legal segregation and rigid racial hierarchy, she lived through the civil rights movement and into an era when at least the formal barriers had been removed, though inequality persisted in other forms. She saw her former students achieve things that would have been impossible in her youth, holding professional positions, earning advanced degrees, contributing to fields from which they had been excluded. Yet she also understood how much remained to be done. Formal integration did not automatically create equal opportunity. Schools in black neighborhoods were still underfunded, still struggling with the legacy of decades of official discrimination. Mathematical education in these schools was still inadequate, limiting students' futures before they had fairly begun. The work of creating true equality required ongoing effort, continuous vigilance, persistent advocacy. In her later years, Euphemia reflected on her long career with a mixture of satisfaction and awareness of unfinished business. She had broken barriers, had educated thousands of students, had fought for justice in educational policy. But she had also spent her entire professional life working within structures of inequality, teaching in segregated institutions, fighting battles that should never have needed to be fought. What might she have accomplished in a society that had valued her from the beginning, that had not required her to spend so much energy simply claiming her right to participate? When Euphemia Lofton Haynes died in 1980 at age 90, she left behind a legacy that extended far beyond her mathematical research. She had shown that excellence was possible despite barriers, that education was both an individual achievement and a collective project, that mathematics could be a tool for social change. The doctorate she earned opened doors for those who came after, demonstrating what was possible. The students she taught carried forward her commitment to education and justice. The policies she fought for helped dismantle formal segregation in Washington's schools. Yet her name is not widely known. She appears in few general histories of mathematics, is absent from most accounts of civil rights activism. She is unsung in the sense that her multifaceted contributions, as mathematician, educator, and activist, do not fit easily into standard narratives that separate these domains. But her influence persists in the lives she touched, in the institutions she helped build and reform, in the example she set of engaged citizenship using all one's capabilities, including mathematical expertise, in service of justice. As you rest in these final moments before sleep fully claims you, imagine Euphemia in her classroom, perhaps in the 1970s, near the end of her teaching career. She is explaining a mathematical proof to students who now include people of all races, teaching in an integrated institution that her advocacy helped create. The mathematics is the same, the logical relationships, the necessary conclusions, the beautiful structure of reasoning. But the context has changed, transformed by efforts like hers. There is quiet triumph in this image, not the dramatic victory of a single moment, but the cumulative effect of decades of patient work, of showing up day after day to teach, to advocate, to build, to challenge injustice wherever it appeared. Mathematics for Euphemia was never separate from life, never an escape into abstraction. It was a tool for understanding, for teaching, for arguing, for demonstrating capability, for demanding equality. In her integration of mathematical expertise with social commitment, we see a model of engaged scholarship, of knowledge put to use in the world, of intellectual achievement inseparable from moral purpose. She was both mathematician and activist, both teacher and advocate, showing us that these roles need not conflict but can reinforce each other, that understanding mathematics deeply can strengthen one's ability to change the world. Marjorie Lee Browne, 1914 to 1979. Our journey continues in the American South, in the mid-20th century, another era of segregation, but also of slow transformation, when historically black colleges and universities provided islands of intellectual opportunity in a sea of discrimination. Here we meet a mathematician who understood that individual achievement, while valuable, was not enough, that lasting change required building institutions, creating pathways for others, establishing programs that would continue long after any individual's career ended. Her name was Marjorie Lee Browne, and she was one of the first African-American women to earn a doctorate in mathematics. But more importantly, she spent her life ensuring that she would not be the last, that the door she passed through would remain open, and that others would have an easier journey than she did. Marjorie Lee Browne was born in 1914 in Memphis, Tennessee. Her mother died when Marjorie was just 2 years old, and she was raised largely by her father, a railway postal clerk who had attended college for 2 years, unusual for a black man in the early 20th century South. Her father loved mathematics and shared that love with his daughter, often spending evenings working through problems with her, fostering in her a sense that mathematics was both beautiful and accessible. This early encouragement proved crucial, giving Marjorie a foundation of confidence that would sustain her through many obstacles. Picture young Marjorie in Memphis in the 1920s, sitting with her father at their kitchen table in the evening, working through arithmetic problems by lamplight. Her father explains a concept, perhaps about fractions or basic algebra, and Marjorie's eyes light up with understanding. There is warmth in this scene, a father transmitting not just mathematical knowledge, but the idea that his daughter is capable of mastering it, that her mind is as good as anyone's, that she should never accept limitations imposed by others' prejudices. Marjorie attended Lemoyne High School in Memphis, one of the segregated schools serving black students, where despite limited resources, she received a solid education from dedicated teachers. She then attended Howard University in Washington, D.C., where she earned her bachelor's degree in mathematics in 1935. Howard was one of the premier historically black universities, with a strong mathematics department that included several faculty members with doctorates from prestigious universities. There, Marjorie encountered mathematics at a more advanced level, studying abstract algebra, real analysis, and other topics that prepared her for graduate work. After Howard, Marjorie taught briefly at Gilbert Academy in New Orleans, then pursued her master's degree at the University of Michigan, earning it in 1939. She then joined the faculty at Wiley College in Texas, teaching mathematics to undergraduate students. But she knew that if she wanted to make the greatest impact, she would need to earn a doctorate. In the 1940s, this was a formidable challenge for anyone, but especially for a black woman. Few universities admitted black graduate students, and those that did often subjected them to discrimination and isolation. Marjorie chose to pursue her doctorate at the University of Michigan, returning there in 1947. She worked on problems in topology, a branch of mathematics concerned with properties of space that remain unchanged under continuous deformations. Imagine Marjorie in Ann Arbor, perhaps one of very few black students at the university, certainly one of very few black women in mathematics. She sits in graduate seminars, participates in discussions, works through difficult problems, persisting despite isolation and the constant awareness that she must prove herself in ways white students never had to. Her dissertation, completed in 1949, was titled On the One-Parameter Subgroups in Certain Topological and Matrix Groups. It was sophisticated work involving the theory of Lie groups, mathematical structures that combine algebraic and topological properties and have deep connections to physics and geometry. The dissertation demonstrated complete command of advanced mathematics and original research, contributing to knowledge in the field. When Marjorie Lee Browne received her doctorate in 1949, she became one of the first African-American women to earn a PhD in mathematics. The same year, Evelyn Boyd Granville also earned her mathematics doctorate from Yale. Two black women achieving this milestone simultaneously, breaking through barriers that had seemed almost impenetrable. But while this was a significant personal achievement, Marjorie understood it as only a beginning. The question was not just what she could accomplish individually, but what structures she could build to enable others. She joined the faculty at North Carolina Central University, a historically black institution in Durham, where she would spend the rest of her career, 30 years devoted to building one of the strongest mathematics departments at any HBCU. Picture Marjorie arriving at North Carolina Central in 1949, surveying the mathematics program, seeing both its potential and its limitations. The faculty was small, the resources modest, the curriculum basic. But she saw what it could become with vision, effort, and determination. Over the following decades, Marjorie worked systematically to strengthen the mathematics department. She recruited faculty, designed new courses, raised standards, secured grants to buy equipment and fund student research. She insisted on rigor and excellence, refusing to accept that her students deserved anything less than the best mathematical education. She mentored countless students, encouraging them to pursue graduate studies in mathematics and related fields, writing recommendations, helping them navigate applications to graduate programs. Imagine Marjorie in her office in the 1950s or 60s, meeting with a talented undergraduate student who is uncertain about whether to pursue graduate study in mathematics. She asks about the student's interests, discusses what graduate school involves, addresses concerns about whether the student is good enough. She shares her own experience, acknowledging the challenges but emphasizing the rewards. By the end of the conversation, the student leaves with renewed confidence and a plan for moving forward. This scene repeats dozens, perhaps hundreds of times over Marjorie's career, each conversation potentially changing a life, opening possibilities that the student hadn't fully considered. But Marjorie was particularly interested in ensuring her students understood not just pure mathematics, but also its applications, especially in the emerging field of computing. In 1960, she obtained a grant to purchase one of the first computers at any HBCU, an IBM 1620, a machine that filled a room and represented cutting-edge technology at the time. This was visionary leadership. Marjorie recognized that computing would transform mathematics and science, and she was determined that her students would not be left behind by this transformation. Picture the computer center at North Carolina Central in the early 1960s, the IBM 1620 humming quietly in a temperature-controlled room, students learning to program in machine language and early high-level languages. Marjorie has arranged for training, has integrated computing into the curriculum, has ensured that her students understand both the mathematical foundations of computation and its practical applications. Some of these students will go on to careers in the emerging computer industry, equipped with skills that make them valuable employees in an economy being transformed by information technology. Marjorie also taught summer institutes for mathematics teachers, helping to improve mathematics education across the region. She understood that strengthening mathematics at the college level required strengthening it at earlier levels as well, that teachers needed support and continuing education to teach mathematics effectively. She gave lectures, led workshops, shared her pedagogical insights, building networks of mathematics educators who supported each other's work. Her commitment extended to using her own resources to support students. She established a scholarship fund with her personal money, providing financial assistance to mathematics students who otherwise might not have been able to continue their education. She didn't publicize this widely. It was simply something she did because she believed in investing in the next generation. After her death, colleagues and former students discovered the extent of her financial support for students, money given quietly over many years. In her research, Marjorie continued to work on topological problems, publishing papers on classical groups and related topics. But she never let research become an escape from teaching and institutional building. She understood that at an institution like North Carolina Central, the primary mission was undergraduate education, and she embraced that mission fully while maintaining her own scholarly activity. She showed that one could be both an excellent researcher and a dedicated teacher, that these roles reinforced rather than competed with each other. Picture Marjorie in the 1970s, now a senior professor, watching with satisfaction as students she mentored years earlier returned to visit, now holding doctorates of their own, now teaching at universities or working in industry, now mentoring their own students. The pathways she helped create are working, multiplying impact across generations. The department she built has a strong reputation, is sending students to graduate programs at major universities, is contributing to diversifying mathematics. Marjorie Lee Browne died in 1979 at the age of 65, her life cut shorter than it should have been, but not before she had fundamentally transformed mathematics education at North Carolina Central and influenced countless students. In the years after her death, the extent of her impact became even clearer. Former students shared stories of her encouragement and support, of how she had changed their lives by believing in them and showing them what was possible. The department she built continued to thrive, training new generations of mathematicians. Yet her name is not widely known outside circles of historians of mathematics and those connected to historically black colleges and universities. She published research papers, but not at the volume that brings fame in the discipline. She won awards, but not the most prestigious national honors. She is unsung in the conventional metrics of mathematical achievement. But by other measures, students mentored, programs built, institutional capacity created, her achievements are extraordinary. Consider what Marjorie understood that many brilliant mathematicians miss. That individual achievement matters less than collective progress, that the measure of a successful career is not just personal publications, but students taught and institutions built, that the point of breaking through barriers is to ensure they stay broken, that true generosity means not just sharing knowledge, but creating structures that will continue sharing knowledge after you're gone. In focusing on institution building rather than just individual research, Marjorie was following a tradition within historically black colleges and universities, where faculty understood that their work was not just academic, but social and political, not just about advancing knowledge, but about creating opportunity and fighting inequality. The mathematics she taught was universal, but the context in which she taught it was specific. A segregated society that systematically denied opportunities to black students, making institutions like North Carolina Central crucial spaces where excellence could flourish despite external barriers. Marjorie also represented a bridge between generations and between different aspects of mathematics. She connected pure mathematics, her own research in topology, with applied mathematics and computing, ensuring her students understood both. She connected the older generation, who had fought initial battles for access, with younger generations who would benefit from the pathways created. She connected individual achievement with institutional development, showing that both were necessary. As you drift into the deepest sleep, into the quiet space where consciousness releases its hold, let the image of Marjorie rest gently in your mind. Perhaps standing before a blackboard, explaining a topological concept to attentive students, or sitting at that early IBM computer with students learning to program, or meeting quietly with a scholarship recipient, assuring them that yes, they belong in mathematics. Yes, they can succeed. Yes, there are people who believe in them and will support them. There is profound satisfaction in this vision. Not the satisfaction of individual glory, but the deeper satisfaction of knowing that your work continues, that the students you taught are now teaching others, that the programs you built are still opening doors, that the pathways you created are carrying new travelers to destinations you might not have imagined, but would surely celebrate. This is mathematics at its most generous, not hoarded or performed for personal recognition, but shared freely, taught patiently, embedded in institutions that will outlast any individual, creating possibilities for others that you yourself may never have fully enjoyed. In Marjorie Lee Browne's life of building and teaching, of research and mentorship, of personal giving and institutional creation, we find a model of mathematical life that measures success not in theorems proved, but in lives changed, not in papers published, but in students empowered, not in individual achievement, but in collective progress toward a more inclusive, more just mathematical community.